Hello and welcome to the eMath Instruction YouTube Live Algebra 2 Regents Review. My name is Kirk Weiler, and tonight we're going to be going through the June 21st, 2023 Algebra 2 Regents exam. If you don't already have a copy of this exam, I'd encourage you to go over to emathinstruction.com. Visit our blog. It'll be the first article right on top. You can go into our blog post. You can open up this particular exam and print it out. It is obviously most helpful if you've actually worked through this exam at this point, so that as I go through each one of the questions, you can kind of understand if you got it right, why you got it right, or perhaps a different approach on how to get it. Or if you couldn't get it right, at least you've tried the problem. Now you get to watch me do it and you can kind of understand. Even though we are streaming live right now from upstate Red Hook, New York, even though we're kind of coming live to you, you can of course pause the video, right? Try a problem and then unpause it and watch as I kind of go through the solution. Now, before we kind of jump in and even start the exam, let me just remind you that at the end of all of your Regents math exams, there is in fact a formula sheet. Now, I'll just say one thing, right? This formula sheet isn't great for any one of the three Regents exams, but it's particularly not all that helpful for the Algebra 2 Regents exam. In fact, there's all sorts of things that you'd kind of wish were on here, but the few things that you might actually use on here, not likely the Pythagorean theorem, although who knows, right? Maybe a little bit of trigonometry work you might have. The quadratic formula, certainly you might need to use. Both arithmetic sequences and geometric sequences could come up in this particular exam, all right? And certainly what you would expect to see somewhere is the sum of what's known as a geometric series right there. Could you have to convert between radians and degrees? Perhaps. But one thing I certainly wouldn't get caught up on at all is this final equation for exponential growth and decay. You're going to have to deal with exponential functions on this exam, and plenty. But one thing you'll never probably have to do is do anything with this particular formula. Anyway, not the point. Let's kind of get out of this thing. Let's get to the beginning of the exam and let's get to it. I've got an exam to work through and a summer vacation to get to. You, on the other hand, have an exam to work through, and then you've got one tomorrow morning that's going to go great. So let's jump right into it, and let's begin this exam. All right, here we go. Problem number 1. The population of Austin, Texas from 1850 to 2010 is summarized in the table below. Over which period of time was the average rate of change in population the greatest? Now, before we even launch into this, let's just take a look at our particular table. One thing that I notice about the table is that the years are going by 20-year intervals, 1850, 70, 1890, 1910, etc., right? And one thing I can see, like most population trends, is that the population is growing, and it's sort of growing faster all the time. Now, they give us all these intervals, and they want to know, when is the population changing the fastest, right? Right, that's what it's asking for. And if all of these intervals were 20-year intervals or whatever, even just the same amount of time interval, right, then you could just look at how much the population has changed, not the rate of change. Unfortunately, when we look at choice 1, 1850 to 1910, right, 1850 to 1910, that's a 60-year interval. Then number 2, 1990 to 2010, that's only a 20-year interval. 1950 to 1970, that's at least a 20-year interval. And 1890 to 1970, that's actually like a much larger interval, right? That's, what is it, 1890, that's an 80-year interval. Now, because the intervals have different amounts of time, you really do have to go through, in a certain sense, and calculate the average rate of change for each interval. So let's take a look at how that's done, at least for choice 1, all right? And then we'll talk about what the correct choice is. So if I'm looking to calculate the average rate of change for 1850 to 1910, right, I'm going to come in here. And of course, the first thing I really need is I need my change in population, which is going to be my 29,860 minus my 629. Remember, essentially what we're doing here is a slope calculation. And then 1910 minus 1850. All right, now before I kind of plug this into my calculator, I just want to mention again, the numerator here, right, is just how much the population has changed as we go from 1850 to 1910. And of course, the denominator is how many years have passed. So I don't really even need that. I could just put down 60 years in the denominator. Now, if I just kind of go into my graphing calculator, right, I can even go do all of this within a fraction bar, and I can just simply take a look and go, all right, I've got 29,860 minus 629, right, the change in population, divided by, and again, you can just put in 1910 minus 1850, which will be 60 years. I hit enter and I get that silly fraction, so I'm going to hit Control Enter, which is going to give me an approximation. And I'm going to just round that to the nearest whole number. I'm going to say that's 487. We'll talk about that in a second. So this is 487 people per year. All right. And again, before we kind of even move on to choice 2, right, let's just talk about this. What this means is that on average between 1850 and 1910, the population is getting larger by 487 people per year. Now, we could do that for every single one of these things, all right? But a savvy student, right, can actually look at this table and go, wait a second. From 1990 to 2010, the population almost doubles. It doesn't double, but it gets much larger over a small amount of time, 20 years. So in fact, in this interval, right, if I just did this for the rest of these intervals, right, this particular one has a rate of change of 14,805 people per year. And it's not even close. That one's 14,805, this one's 5,967 people per year, and this one is 2,965 people per year. So if you calculate that average rate of change for each one of these intervals, the one that wins hands down is 1990 to 2010. And that's because what we have here is sort of an exponential population growth, so it's growing the fastest right at the end. That wouldn't necessarily have to be the case, so you could have a situation where, you know, maybe it's growing faster, then it's growing slower, etc., but not in this situation. So let's take a look at problem number 2. Which expression is not, and this is important, which of the expressions is not equivalent to 36x to the 6th minus 25y to the 4th? All right, and they've just got all sorts of things here. Now, one thing that I noticed right away with this, 36x to the 6th minus 25y to the 4th, is this really has the structure of the difference of perfect squares, right? The difference of perfect squares, that thing that basically says, if I have m squared minus n squared, that's m minus n times m plus n, right? That's what it is, right? And I know that this is the difference of perfect squares because 36 is 6 squared, right? So this thing is literally 6 squared, and then I've got x to the 3rd squared minus 5 squared times y squared squared. And so, by the way, that's just simply this first one, right? That one is equivalent, right? But then if I factored this using the difference of perfect squares, right, what I would end up getting is I would get 6x cubed minus 5y squared times 6x cubed plus 5y squared. That would be kind of your straight up factoring, and that would be choice 2. All right, so that one is also equivalent. And then I look at choice 3. 6x to the 6th minus 5y to the 4th times 6x to the 6th plus 5y to the 4th. Well, if I actually multiplied those out, I would get 36x to the 12th minus 25y to the 8th, right? So this thing, maybe put it in red, given that I'm getting this all marked up everywhere. This is our winner because ultimately, if I multiplied that out, I would get 36x to the 12th minus 25y to the 8th. And that would obviously be incorrect. That would not be the same. All right. Let's take a look. Let me go back to blue really quick. And let's take a look at number 3, which I really like this problem. Let's take a look at it. What are the zeros of s of x equals x to the 4th minus 9x squared plus 3x cubed minus 27x minus 10x squared plus 90. All right, so first off, I've got my bell chair. All right, so to begin with, right, just the term zeros, right? The zeros of any expression are literally the solutions that we get when we take the expression and we set it equal to 0. Right? So literally, this is what it's asking us to find. Now, I would be remiss if I didn't say right away, one way to do this problem is to go into your graphing calculator, which we're going to use tonight, the TI Inspire, put this expression in as if you were going to graph it, look at a table of values, and see which x values give you a y value of 0. All right, it's a legitimate way of doing it. It's very simple, it's elegant, it's great. I looked at this thing and immediately, I started being like, let me combine some like terms. Let me take negative 9x squared and negative 10x squared and make them into negative 19x squared, you know, and let me do a bunch of different things like that. That's actually the only thing I can do. And then I kind of got stuck. And then I looked at it and I said, wait a second. I see something. I see a structure here, all right? I think I can group these two together, and then I'm going to group these two together. I'll put a little plus right there. And what I'm going to do is I'm going to factor each one of these binomials. The first one, I'm going to factor an x squared out of, and I'm going to be left with an x squared minus 9. The second one, I'm going to factor a 3x out of it, and I'm going to be left with an x squared minus 9. And the last one, I'm going to factor a negative 10 out, and I'm going to have x squared minus 9. Right? And all of a sudden, I see a common factor of x squared minus 9. So let me keep going. I'm going to extend the page a little bit. All right, so now I'm going to factor an x squared, I'm going to try to factor an x squared minus 9 out of each one of these. And I'm going to get this. And of course, I've got my favorite mystery red pen just jumping out today. It's awesome. All right, but the cool thing is now I can go back to Algebra 1. I know how to factor x squared minus 9. X squared minus 9 is x minus 3 times x plus 3. I also know how to factor x squared plus 3x minus 10. That's going to be x plus 5 times x minus 2. And now I've used the structure of this expression to completely factor it, and because I know the connection between factors and zeros, I can now say this one will give me a 0 of x equals 3. This one gives me a 0 of x equals negative 3. This one gives me a 0 of x equals negative 5. And this gives me a 0 of x equals 2. And therefore, my correct answer after all of that is choice 4, negative 5, negative 3, 2, and positive 3. Kind of pretty, right? So look for that. If they give you a really complicated looking polynomial expression and they ask you for the zeros of it, try to be as flexible as you can with your factoring. You know, try factoring by grouping, you know, especially if there's an even number of terms, 4 terms or 6 terms, consider doing that. And we'll see another example a little bit later on where we want to look for structure and use that to then do some factoring. For now though, let's move on. All right, number 4. If theta is an angle in standard position whose terminal side passes through the point negative 2, 3, what is the numerical value of tan theta? All right, this is a very fair question. It's our first trig question on the thing. The one thing I don't love about this is that they've oriented us on a circle that is not the unit circle, but that's okay. We can still think about it quite similarly, all right? If I sort of put myself on a circle like this, and I ended up sort of having this terminal ray that goes through the circle, and specifically passes through the point negative 2, negative 3, I can still think about this the way I've thought all the way through trig, which is that really what I have is I've got this right triangle, right? Now this entire angle is my theta, but this angle just down in here is my reference angle, right? Theta reference, theta sub r, okay? And remember what we now have is we've really got sort of this right triangle where we've got a base equal to negative 2, and if you will, a height equal to negative 3. Remember that we define tangent really from geometry. TOA. Tangent is opposite divided by adjacent. So opposite of that angle is -3. Adjacent to that angle is -2. A negative divided by a negative is a positive. And so the tangent of theta here is +3/2. Basically, tangent will always be y over x, right? On the unit circle, y is sine and x is cosine. So tangent is defined as sine divided by cosine on the unit circle. But on any given circle, you can always determine what the tangent value will be by simply taking the y-coordinate and dividing it by the x-coordinate. That will be rise over run, slope, or the tangent function. Talking about trigonometry, let's take a look at another trig problem. Exercise number 5. The average monthly temperature, T of m, in degrees Fahrenheit over a 12-month period can be modeled by T of m equals -23 times the cosine of pi divided by 6 times m plus 56, where m is in months. What is the range of temperatures in degrees Fahrenheit of this function? Fantastic. There's not a lot of trig in Algebra 2, even though some of you may have even called this course trig. Little ironic there. But one of the things they do want you to be able to do is look at what are called sine and cosine models, or sine and cosine functions, and identify basic things. For instance, right, 56. Y equals 56 is what's called the midline of this function. Okay? And A, absolute value of A, equals 23, is what's called the amplitude. All right? Don't even worry about the pi over 6. It's somewhat irrelevant. All right? We've got 56 as the midline and 23 is the amplitude. In other words, 56 is this horizontal line, and the curve goes 23 above it and 23 below it, and 23 above it and 23 below it. So again, you've got some horizontal line, y equals 56, and this thing is going, 23 above, 23 below, 23 above, 23 below, like this. Doesn't matter that it's a -23, okay? That just tells us that it starts at a minimum instead of a maximum. So what is our range in temperatures? Well, our lowest temperature, y min, will be our midline minus the amplitude, which is going to be 33. And our maximum is going to be our midline plus our amplitude, always. And that's going to be 80, oops, nope, sorry about that, not 80, is going to be 79. So we should have choice 2, 33 to 79. All right, be prepared for that most certainly, right? If you're given a sine or a cosine function, be prepared to be able to look at its midline and add its amplitude and subtract its amplitude, which is always the absolute value of the number that's multiplying the sine or the cosine, always. All right, the absolute value, right? The negative and positive just determines whether it starts sort of up or down or, inverts or whatever. All right, let's take a look at number 6. Which expression is an equivalent form of a times the 5th root of a to the 4th? All right. Well, one of the things you need to be very careful on here is it's easy to look at this expression and think you're doing a to the 5th times the square root of a to the 4th. But that's not what we have here, right? What we have is a times the 5th root of a to the 4th. Now, a is, of course, just the same as a to the 1st. And the 5th root of a to the 4th is the same as a to the 4/5. Whoops, not to the 4/3. Let's try the 4/5. There we go. So we have this beautiful exponent rule that then says if I multiply two things together that have the same base, and here they have a base of a, then I can simply add their exponents. So I'm going to get a to the 1 plus 4/5, which is equal to a to the 5/5 plus 4/5, which is a to the 9/5. Choice 2. All right. Awesome. Let's take a look at the last problem on this sheet, number 7. The expression 3i times a times I minus 6i squared is equivalent to which of the following? All right, now normally in this type of a problem, they will be very clear about saying that I is the imaginary base. They didn't do that here, but they are most certainly kind of implying that. So in this case, right, this is where we're looking at this fact that we've got I, which is the square root of -1, I squared, which is negative 1, I cubed, which is negative I, and I to the fourth, which is equal to 1. So this is what's called the cyclical nature of the powers of I. I defined as the square root of negative 1, I squared is negative 1, I cubed is negative I, and I to the fourth is 1. So now let's take a look at how we can simplify this particular problem. Right? If I have 3i times ai minus 6i squared, and I distribute through, I'm going to get 3ai squared minus 18 times I cubed. Well, I squared is equal to negative 1, and I cubed is equal to negative I. And you have to be a little bit careful here because, you know, what you've got is you've got negative 18 times negative I. And negative 18 times negative I almost looks like it's 18 minus I, but it's not. It's just going to be negative 18 times negative I, which is going to be negative 18, right? Here, of course, we have 3a times negative 1, which will just become negative 3a, all right? So at the end of the day, right, we can extend this page a little bit. This will become negative 3a. This will become plus 18i. And that will be right here, negative 3a plus 18i. Done, right? And again, this one's a little bit tricky because obviously your calculator can do a lot of arithmetic for you in terms of imaginary numbers, right? All of the modern graphing calculators have I on it, and you can put it into complex mode, and you can have it tell you what I squared is and I cubed and things like that, all right? But you know, that a being thrown in here makes it a little bit more difficult. Okay, let's keep going. Number 8. Number 8 is a sheer pleasure for me because when I looked at it, right, and let's take a look. Number 8, which equation best represents the graph below? And then there's 4 choices. H of x equals log of x plus a plus c. H of x equals log of x minus a plus c. H of x equals log of x plus a minus c, and h of x equals log of x minus a minus c. Now, one thing that we can tell by just looking at this graph is that a is supposed to be a positive number and c is supposed to be a positive number. Now, what is certainly true, though, is that they never ever told us anything about how big a is compared to c. All right. That being said, let's just take a look at something, because something smelled a little bit funny about this problem to me right from the get-go. Now, hopefully everybody is comfortable with the fact that this is log base 10, but even if it weren't log base 10, all right, all logarithm graphs basically look like this if the base is bigger than 1, and obviously 10 is bigger than 1. All right, now, what does it mean by they look like this? It means that they have a vertical asymptote at the y-axis, meaning that they bend vertically as they approach the y-axis. This one has clearly been shifted by a units to the left. Clearly been shifted by a units to the left, all right? Now remember, in order to shift something to the left by a units, we will have to add a to the x directly. So one thing is of no question in my mind whatsoever, which is that this has got to be, at the bare minimum, y equals log base 10 of x plus a. All right, because it's been shifted again, a units to the left. Now notice, without shifting it anything up or down, it kind of almost appears that the graph has sort of gone up, right? Just by the sheer fact that we've sort of shifted it to the left. So now the question is it plus c or is it minus c, right? Have we added something and shifted it up, or have we subtracted something and shifted it down? Well, the official answer to this question is choice 1. The problem is it can be either choice 1 or choice 3. I don't think they even ever put out a correction on this. Now you might be like saying, well, no, it can't. They've definitely shifted it up 1 unit. Just remember, right? We don't know what c and a are. We just know they're both positive numbers. So just for a moment, right, I want to show you something. All right, here we go. Here's the problem, all right? log base 10, where I've put C equals to, A is 2, and I put C in as 1. So I like literally looked at their graph, and I just said, hey, let me just assume that this grid is what it is. So C is 1, A is 2, right? And I then put in y equals log base 10 of x plus 2 plus 1, and look, that looks right? That looks like the graph. So it's got to be log of x plus a plus c. But wait a second. Hold on. Look at the blue, look at the red, look at the blue, look at the red, look at the blue, look at the red. All right, look at this one. This is log base 10 of x plus 200 minus 1. Wait a second. That looks perfectly good. That looks like this. And that's of this form. Log of x plus a minus c. Right? So it could really be either choice 1 or choice 3. And again, it's a little disappointing, honestly, of the test makers, right? Because I immediately realized, at least for me, that if I shift a logarithm graph enough to the left, right? If I shifted this 10 million units to the left, again, a could be anything, we have no idea, then this thing is going to be huge. It's going to be like way up here, and then I could subtract and it would still be up here. It'd still be up there. And again, it took me absolutely no time to be like, oh, let me just come up with one. Let me just shift it 200 units to the left and 1 unit down. And we then get a graph that looks exactly like basically this graph, where I've shifted it 2 units to the left and 1 unit up. The only difference is that the scale on the x-axis is different in this graph than it is in this graph. But then again, if they didn't want the scale to be different between the two, then they should have just said A is 2 and C is 1. And they didn't do that. So really, this particular problem, they want you to say choice 1, but there's absolutely no way to know whether this has been shifted vertically up, shifted vertically down, or C could just be 0. C could be 0. I could have not shifted this up or down whatsoever. All right, that being said, everybody makes mistakes. Let's take a look at question number 9. Which function has the characteristic that as x approaches negative infinity, f of x approaches negative infinity? All right, so let's interpret this. This is what's called end behavior or long run behavior. End or long run behavior. All right, and specifically there are 2 types of long run behavior. There's the kind of behavior that occurs when x gets just larger and larger, it heads off to infinity. And then there's the behavior of when x goes to negative infinity, when it keeps going to the left. So basically what this says is as x goes to the left, y needs to always be going down. Always needs to be going down. It's got to be heading towards negative infinity. So as x goes to the left, y has to be heading down. Well, look at this graph. Here, as we go to the left, the graph is heading up. So in this particular graph, as x goes to negative infinity, f of x is going to positive infinity. All right, let's take a look at the other graph they give us. Same song, second verse. If I go to the left here, the graph is heading up. So yet again, we've got a graph where as x goes to negative infinity, y is going to positive infinity. Fair enough. Let's take a look at this one where they don't actually give me the graph, but they give me the equation. Now, of course, one option here is to put that into your graph, into your calculator, and graph it. But I'm kind of hoping that many of you see this one and you say, oh, that's a decreasing exponential. In other words, choice 4 looks something like this. Kind of goes like that. That's a decreasing exponential. So yet again, as x goes to negative infinity, y is going to positive infinity, right? Again, the wrong behavior. So it's got to be number 4. It's got to be f of x equals negative log base 5 of negative x. Now, that one, I even looked at it and I was like, well, by process of elimination, that one's got to be the right one. But let me kind of show you, without even putting it into the calculator, why it's got to be the right one. I'm going to walk you through a couple transformations. We just talked about what a generic log graph looks like. So if I just was looking at y equals log base 5 of x, and it really doesn't matter if it's log base 5 or log base 10 or log base 2, as long as the base is greater than 1, generally speaking, the graph is going to look like this. Okay, so that's log base 5 of x. Now, as soon as I negate the x, then what happens is it looks like this. It reflects it across the y-axis. So this is now log base 5 of negative x. Let me just do that. All right, so as soon as I negate the x, it flips it across the y-axis, and now I have this. But then if I negate that one to have negative log base 5 of negative x, then it will flip this thing like this, and it'll look like this. So this now is y equals negative log base 5 of negative x. And this is what you would see. Let me actually put it in red just so you realize what our final one is. That's our final one. And this one, most certainly, as x is heading to the left, this one is continually going down. All right, so it's heading towards negative infinity. So choice number 4. Okay, let me go back to blue. Back to blue. All right, let's take a look at number 10. The expression x squared plus 3 quantity squared minus 2 times x squared plus 3 minus 24 is equivalent to which of the following? All right, similar to that problem on the first sheet, which I think was problem number 3, where we had to find the zeros of an expression. This is another one where we want to see the structure of what's going on and use it to make something that looks really kind of scary into something rather easy. So here's what I see. I see something squared minus 2 times that same thing to the first minus 24. So in other words, this very complicated structure is exactly the same as this structure as long as m is equal to x squared plus 3. Right? These two things are the same, right, if we combine them. So if I took this thing and I factored it, right, that's pretty easy. I can do that right back from Algebra 1. Two numbers that have a product of negative 24 and a sum of negative 2 will be m minus 6 times m plus 4, right? And now we can just put x squared plus 3 in for m and for m. So we get x squared plus 3 minus 6 times x squared plus 3 plus 4. And that's going to be x squared minus 3 times x squared plus 7. Choice 2, right? Look for structure, all right? Almost all the factoring that you will end up having to do won't really be harder than what you did in Algebra 1. The key is, right, they're going to force you to kind of think about what you're seeing, right, and see that structure that's kind of embedded, right? This is no more challenging than factoring m squared minus 2m minus 24 from Algebra 1. It just looks worse because they put those binomials in there. All right, let's take a look at number 11. What is the solution for the system of equations below? All right, now let me just kind of, before we even get to this, because I'm going to need some room. Yes. And I just got some room. All right, let's talk about this. Now, one thing that, before I go into the algebra, one way of doing this problem is taking each one of these 4 choices and substituting them into each one of these 3 equations to see which one of the choices makes all 3 equations true, right? Because that's the solution to a system. The solution to a system is the point or points that make all the equations of the system true. Now, up to Algebra 2, the only systems you ever dealt with were 2 equations with 2 unknowns. And then Algebra 2 comes along and you have to deal with 3 equations and 3 unknowns. And again, one very fair way of doing this, because you have 3 hours for this test, is to take this thing, choice 1, put it into all 3 equations. See if they're all true. If they're all true, guess what? You're done. It's choice 1, move on. If it's not, then you got to look at choice 2. And as soon as you see one equation that doesn't work, it's a done deal. You move on to the next one. So now let's talk about how we can actually solve it algebraically. And this one's not too bad, okay? What I'm going to do is I'm going to call these equations 1, 2, and 3. And one thing that I notice is that equation 1 has a plus z in it, equation 2 has a minus z in it, and equation 3 has a plus z in it. All right, so the first thing I'm going to do is I'm going to add equation 1. I'm going to take equation 1 and I'm going to add equation 2 to it. And that's going to give me a new equation. When I do that, I have x plus x, which is 2x, y minus 2y, which is negative y, and z plus negative z is 0, so those go away. 2 plus negative 4 is negative 2. Now I'm going to do the same, and I'm going to add equation 2 to equation 3. And when I add equation 2 to equation 3, I'll get x plus x, which is 2x. I'll get negative 2y plus negative 9y, which is negative 11y. And I'll get negative 4 plus negative 18, which is negative 22. And now I have two equations with only two unknowns. And what's cool is they both have a 2x in them. So what I'm going to do right now, and this is a little sleight of hand, but I hope you're okay with it, is I'm going to multiply this entire second equation by negative 1 so that I have a negative 2x here and can add it to this positive 2x and eliminate the x's. So again, I'm going to multiply this entire equation by negative 1, which changes the signs on everything. And then I'm going to add those two equations together. That's going to cancel. Negative y and 11y gives me 10y. Negative 2 plus 22 gives me 20. Divide by 10 on both sides, and y is equal to 2. Awesome. So now let's eliminate every choice where y isn't equal to 2. Okay, that didn't get rid of many. All right, but it got rid of one of them at least. Now, how do we figure out what x and z are? Well, I can now take y equals 2, and I can either put it into this equation or this one. I'm going to put it into this one. I know I just have a line through it, but I think you'll handle it, right? I've got 2x minus y, which is negative 2, equals negative 2. All right, I'm going to now just solve this for x by adding 2 to both sides. That's going to give me 2x is equal to 0, right? Negative 2 plus 2 is 0. Divide both sides by 2, and x is now equal to 0. So now, right, now I have y equals 2, x is equal to 0. So now let me get rid of all choices where x isn't 0. So that gets rid of that one. All right, one more. I need to figure out what z is. But now I can take this first equation, x plus y plus z equals 2, and I can put y equals 2 in and x equals 0 in, right? So I'll get 0 plus 2 plus z is equal to 2, right? So I can subtract 2 from both sides, and I'll get z is equal to 0. So in fact, it's choice 3. Done. Took up a lot of room, but done. All right. Now, I know some of your teachers have shown you calculator tricks involving what are known as matrices and reduced row echelon form and some things that other techniques that if I try to show people them right now, they'd probably just result in crying. So we're not going to do that. Look, if you don't know the algebraic way of doing this, take each one of these points, substitute it in, and what you'll find is it's only choice 3 that makes all 3 equations true. You got plenty of time to do it that way. I encourage you to, if this doesn't look familiar or is too confusing. If you know a calculator trick, hey, more power to you. All right, let's take a look at the next problem. 12. The roots of the equation x squared minus 4x equals negative 13 are which of the following? Now, if you notice, right, when I look at the answer to this question, 3 out of the 4 of them involve I, the imaginary base. So in all likelihoods, we're going to have an I show up in this particular problem. Now, a lot of students, understandably, are going to go with the quadratic formula on this. I actually think I'm going to do completing the square. All right, because I think it's actually easier. So what I'm going to do is I'm going to take this particular problem right here, x squared minus 4x equals negative 13. I'm going to do a little completing the square, right? What I'm going to do is I'm going to take half of negative 4, which is negative 2. I'm going to square it, and I'm going to get 4, and I'm going to add 4 to both sides. I wouldn't do this, by the way, if the coefficient on the x wasn't even. You know, if that had been negative 5x, negative 7x, positive 3x, forget about it. I don't want to deal with fractions here. But as soon as I saw that negative 4, I knew I could easily divide the coefficient by 2, square it, and add it on. And again, you remember the whole deal with this. That's just so that I can now write this as x minus 2 squared. And of course, all of that's going to be equal to negative 9. Right? And I would much rather solve this than have to go through the rigmarole of the quadratic formula. Let me just kind of get rid of this now that we've passed that problem on by. Hopefully you got all of that down. So I can now take this little guy, bring them up here, and now I'm going to do the square root of both sides. That's going to give me a plus minus. X minus 2 is plus or minus the square root of negative 9. That's where that I is going to come in. I'm going to get negative x minus 2 is equal to plus or minus 3i. So x will be 2 plus or minus 3i. Choice 1. Now again, nothing wrong with bringing the 13 to the left-hand side, having x squared minus 4x plus 13 equals 0, and going through your quadratic formula and all of that business. It'll work just fine. But there's a lot of simplifying there. You got to simplify a radical, you have to simplify a fraction, all sorts of stuff. So I would definitely advise you, if you've got a situation where completing the square is easy, leading coefficient is equal to 1, and the coefficient on the x term is even, right? Then completing the square, in my personal opinion, is a lot easier to do than the quadratic formula. All right, let's take a look at a polynomial long division problem. Exercise number 13. Which expression is equivalent to 2x to the third plus 2x minus 7 divided by 2x plus 4? All right, now I know that this is polynomial long division as opposed to just simplifying a rational expression, because all of these have sort of a fractional remainder going on here, right? Minus 27 over 2x plus 4, minus 3 over 2x plus 4, etc. So I'm going to review for you now how to do polynomial long division. And again, I'm going to get rid of that. Now, one of the things that they did that was a little bit tricky in this problem, and a very similar problem showed up on our last review a year ago, and they didn't do this, is that notice the numerator is 2x cubed plus 2x to the first minus 7. They don't have an x squared term there, but you need to have it in order to do polynomial long division. So what I'm going to do is I'm going to write the following down. 2x cubed plus 0, x squared plus 2x minus 7, and now I'm going to divide that by 2x plus 4. All right, let's review how to do polynomial long division. So the first thing I need to do is I need to get rid of 2x cubed. So I look at the 2x, don't worry about the 4, never worry about this, this is totally irrelevant for right now. I'm going to look at that 2x and that 2x cubed, and I'm going to say to myself, what do I have to multiply 2x by to get 2x cubed? And that's going to be x squared. Now, I'm going to put that x squared right there, and then I'm going to multiply x squared by 2x plus 4, and I'm going to get 2x cubed plus 4x squared. Now, just like normal long division, which I realize it's been years since you've done, I want to subtract this from this. What I always tell my students is that easier than that, change the sign on both of these and then add. All right, so whatever it is, what I always kind of do, let me actually go with a different color to just really highlight this, is I just come in here and I do something like this. I just change the two things, and instead of like subtracting, I then add. And that way, if I've got some kind of double negative, it's not a problem. That's not really an issue here, but when I add these two together, these eliminate. 0x squared and negative 4x squared is negative 4x squared. And then I'm going to drop this down, plus 2x. All right, so always, just like polynomial, or just like normal long division, that drops right on down. Now I'm going to do the same game. I'm going to look at negative 4x squared, I'm going to look at 2x, and I'm going to go, what do I have to multiply 2x by to get negative 4x squared? And that's going to be negative 2x, right? So now I'm going to take that negative 2x, just like I did before, and I'm going to do negative 2x times 2x, and that's going to give me negative 4x squared. Then I'm going to do negative 2x times positive 4, that's going to be negative 8x. I'm going to give myself a little bit more room. I'm going to do this. Yet again, just like before, what I want to do is I'm going to change the signs on both of them and add, because what I want is I want like a negative 4x squared and a positive 4x squared to cancel. So I'm just going to add, and when I add those two together, those cancel. I'm going to get 10x and minus 7, right? So now, what do I have to multiply 2x by in order to get 10x? That's just going to be a plus 5. And when I do that, 5 times 2x plus 4, is going to be 10x plus 20. One last time, right? I want to eliminate the 10x's, so I'm going to be a negative and a negative, and when I add those together, that's going to cancel, and I'm going to be left with a negative 27. So what's my final answer? My final answer is this polynomial, x squared minus 2x plus 5 minus 27, all divided by 2x plus 4. And that is choice 1. All right, little polynomial long division. I think this would be a great opportunity to have a little lemonade. That's right, it's our first break. We've been going for about 45 minutes. We've gotten through 13 multiple choice problems. We're moving right along. Ah, lemonade. During my geometry review, I mentioned the fact that last week at one point in time, I played a little bit too much pickleball and pinched a nerve in my lower back called the sciatic nerve. So I've got like all sorts of like weird left leg issues going on. I could just fall in the middle of this thing like right over. Ibuprofen. Again, still ibuprofen. It's a boy's best friend during this review. It's absolutely wonderful. So, you know, we're gonna get through this review, hopefully on our feet, especially since I'm talking about myself as if I'm more than one person. And then I'm gonna take, hopefully, the next few weeks to slowly recover. All right. Anyway, it's been fun, you know, trying to recover from a pinched nerve in one's back. I highly suggest avoiding it until you're middle-aged. Lemonade. I'm not going to miss the pickleball season, though. I'm going to get there. I'm going to be ready for the 2028 Olympics when pickleball is finally an Olympic sport. I don't think it will be in 2028, but it should be. All right. Yeah, you never know. Yeah. Things come, things go. Breakdancing, that's a sport this year. Karate's out, breakdancing is in. I know, breakdancing. They just call it breaking though, you know what I mean? I would think breaking would be like breaking boards or something like that, but no, it's the sport of breaking. Anyway, as a child of the 1980s, I'm very excited that breakdancing is part of the Olympics. I hope that parachute pants are as well. So let's get right back to it. Number 14, that was for all people of my generation. A popular celebrity tracks the number of people in thousands who have followed her on social media since January 1st, 2015. A summary of the data she recorded is shown in the table below. So number of months since January 2015, number of social media followers in the thousands, by the way. She doesn't have 3.1 followers after 2 months. She has 3.1 thousand followers after 2 months. In other words, 3,100 followers. All right. And what are they going to ask us? The celebrity uses an exponential regression equation, of course she does, to model the data. According to the model, how many followers did she have on June 1st, 2018? All right, by the way, we have our winner. This is our winner for the biggest pain of a multiple choice problem on the test. This is our winner right here. Do you know what I mean? So let's talk about this, right? This is our one regression problem on the test, okay? And it doesn't just end with regression, but that's where it begins. So what do? Well, we've got our TI, right? And you know, one of the things that we want to do on the TI is we've got to be able to get the data in. All right, so on the TI Inspire, you do it one way. On the TI 84, 83, you do it another way. On the Casio, you do it a certain way. On Hewlett-Packard, you do it another way. Anyway, in the TI Inspire, you put the data in a way that's sort of like a spreadsheet. It really does look like a spreadsheet. And I always love to actually label the X data and the Y data. So the X data was the number of months, you know, and then the Y data was the number of followers. And of course, when I put this in, I have to check really carefully that it's correct. All right, I want to make sure all these numbers have been put in correctly, because if I don't do that, then what's going to happen is I'm going to get a terribly incorrect answer. All right, and then I won't have one of the 4 choices and I'll be completely and utterly confused. And if it's free response, then I'm in real trouble. All right, but assuming that all my data is in there incorrect, then what I'm going to do is I'm going to hit my menu. I'm going to go to choice 4, which is statistics. I'm going to go to statistical calculations, and what I want is exponential regression. If you have to do regression on this test, in all likelihood, it will be exponential regression. It won't likely be linear. That's really Algebra 1, okay? It will likely be exponential, not tend to be anything else. So I'm going to go with exponential regression. Now, it asks me for my X list. This is where I really like to have these things labeled. So what I'm going to do is I'm going to go for months for my X list. My Y list, I'm going to go for followers. I'm going to save my regression equation in, it's not going to let me do it, Okay, I'll just save it in F2. That's because apparently there's already something in F1. It's not going to let me get out of here. Here we go. And I'm going to hit OK. One more time. Yes. Okay, excellent. Whew. So after all of that, right, an exponential regression equation, or an exponential equation in general, has the form y equals a times b to the x. A times b to the x, where this is a and this is b. Don't worry about r squared or anything like that. Now, how many decimal places should you take it? Well, I actually took it out like 3 decimal places on each one of these, and it still made my answer relatively not great. All right, so, and here's what I mean by that. If I go back here, right, what I did, I literally took my exponential regression equation out to this level of accuracy. Y equals 1.768 times 1.185 to the x. That's more or less like what the regression equation was. There almost went the leg. All right, now, believe it or not, I really could use to take it out at least 1 or 2 more decimal places, but we'll leave it at that. Because if that was enough, you know what I mean, it would be like, okay, great, I had to put the data in, I had to do the exponent. But now I actually have to use the equation to predict how many followers she has on June 1st, 2018. What in the world is the value of x at that point? Well, where do we start? What is x equals 0? Right, x equals 0 is January 1st, 2015. January 1st, 2015. So I want you to think about this. We have all of 2015, that's 12 months. Remember, x is months. All of 2016, that's 12. All of 2017, that's 12. And now we have, right, on my fingers, that's right, January, February, March, April, May, June 1st, right? We've got, well, actually, we don't go through June. Right? It's actually, we go through January, February, March, April, May, right? And then that's it. So we've just got another 5 there. So that's 41 months, right? 41 months that we're going, okay? So I now take 41 and I put it up into that equation. All right, and actually let me kind of go over back to here. Hopefully back to it one more time. I just go into here. Let me just put this in. Now watch. Remember, x was 41. Remember, this won our award for biggest pain in terms of the problem. So there's our exponential regression equation, 41 months. And that's the answer. 1,861? That's weird. Let's go back to here. Actually, let me say 1,862. All right, and then you look at this and you go, that's not one of the answers, 1,862, except this is in thousands of followers. This is in thousands of followers. That's not how many followers she has. That's how many thousands of followers she has. So if you actually want to know how many followers she has, you tack on another 3 zeros and you have 1,862,000 followers. Well, which one of this is closest to 1,862,000? Well, that one. That's 1,850,000. And it is pretty much almost exactly 1,850,000 if you took the exponential regression equation and you used absolutely every decimal place that the calculator gives you. If you do that, then you pretty much nail this right down. But who in the world would do that? I mean, I'm even tempted to not even go 3 decimal places, but only go 2, and then it'll be really off, you know? So anyway, yes, we can all understand now why that wins the Kirk-Weiler Award for the biggest pain of a multiple choice problem. All right, number 15. Luminescence is the emission of light that is not caused by heat. It's a great word. A luminescent substance decays according to the function below. I equals I sub 0 times e raised to the 3 times negative t divided by 0.6. This function can be best approximated by which? Now, one of the things that's interesting about this is the fact that it can be best approximated by, all right? Kind of meaning, right, that there's like one of these, none of these answers, or whatever the correct answer is, isn't exactly equivalent to this. Now, I think one of the hardest parts of this is really being able to look at this expression and just understand what it is, right? So let me just take this for a second, this thing. Because first off, this almost looks like it's 3 minus t divided by 0.6. But it's not. This is 3 times negative t divided by 0.6. Even better yet, we could bring that 3 inside, and this will be negative 3t divided by 0.6. But let's take it even farther than that. Let's figure out what negative 3 divided by 0.6 is. Just in case you don't know off the top of your head. I wasn't really thinking about it very much. Negative 3 divided by 0.6 is negative 5. All right? So all of this idiocy is equal to negative 5t. All of this junk, all of that exponent, all of this is just negative 5t. So that means that this entire function, right, is I equals I sub 0 e to the negative 5t. Make sure that looks like a negative 5. Okay, now I look at these 4 choices, and I'm so tempted to go with choice 2. You know what I mean? Because the only difference between choice 2 and the thing that I just got was that this is e to the positive 5t, and this is e to the negative 5t. And I cannot emphasize how different this function is than this function. This function is a decreasing exponential. This function is an increasing exponential. They could not be any more different. So, how do I get the final answer? Well, this employs a very common trick, right? Now remember, we've got this exponent property that says when I have something raised to an exponent raised to another exponent, I can multiply those exponents together. Okay, x to the a raised to the b is x to the a times b. But here, I'm going to unmultiply them. In other words, I'm going to rewrite this as I sub 0 times e to the negative 5, all raised to the t. I'm unmultiplying the negative 5t. I sub 0, e to the negative 5 to the t. And now let me take a look at what e to the minus 5 is on my calculator. Let's take a look, and let's just go to a new screen. Here's my e to the negative 5. So e to the negative 5 is 0.006737, etc. Right? So keep that number in mind. That now is I sub 0 times 0.0067 to the t. And there it is. That's the whole deal, right? And what's really unfortunate is just kind of how ugly they make this thing. Now again, I kind of understand why they're doing that, but ultimately the real kind of exponential manipulation work comes right here to here, right? And then going from here to here. All of this rigmarole, believe it or not, is kind of middle school fraction work in a certain sense. But a lot of students, because they're still a little bit unsure about fractions, even at this level, and I get that, right? They can definitely be confusing, right? But because of that, you'll get people that can't even get from here down to here, right? And if you can't take this thing and write it as negative 5t, it's going to be awfully hard to get all the way to choice 3. Now, of course, one thing that you could try to do, you could like ignore the I sub 0 and sort of put this in as a graph and then put all of the other 4 in as the graph and then just see which one is equivalent to it. All right, let's take a look at a statistics question. Let me extend the page a little bit so we'll be able to see this a bit better. Number 16. The heights of students at Central High School can be modeled by a normal distribution with a mean of 68.1 and a standard deviation of 3.4 inches. According to this model, approximately what percent, should be percentage, what percent of the students would have a height less than 60 inches or greater than 75 inches? All right, awesome. This is what's called a normal distribution problem. We're going to see another normal distribution problem, actually, number 17, the next one up. All right, but let's take a look at this one. The normal distribution, also known as the bell. Now, in a normal distribution, the shape and the spread of it are all sort of dictated by the mean, which is 68.1, and the standard deviation, which is sort of a distance away from a mean, which is, in this case, 3.4. And we'll talk a little bit more about standard deviation and the normal distribution in the next problem. All right, but the idea is if you know that a variable is normally distributed, and you know what its mean is and what its standard deviation, you can find the percentage of that population that falls within certain intervals. This one's a little bit tricky though, because we want the percentage of students that have a height less than 60, so maybe 60 would be about here. So we want all these students, all right, and then we want also all of them that have a height greater than 75, which might be out here. Let me put that down there. All right. So we really need to figure out the percentage of students that are in this tail end, the percentage that's in this tail end, and then add them together. Let's talk about how we do that using the TI Inspire. All right, so going into the TI Inspire. All right, what I'm going to do is I'm going to be hitting my menu, okay, and what I need is statistics, choice number 6. All right, what I'm going to then do is I'm going to go to statistical, actually I'm going to go down to distributions. All right, because this is a normal distribution. And I want normal CDF, never PDF, always CDF. Okay, and when I choose that, it wants 4 different things. A lower bound, an upper bound, mu, which is the mean, and sigma, which is the standard deviation. Now, if they had just said, right, if this problem, going back to it, was just how many students or what percentage of the students was between 60 and 75, then 60 would be your lower bound and 75 would be your upper bound. You'd put 68.1 in as your mean and 3.4 in, as your standard deviation, and you'd get your percent. But here we want everything below 60. So what do we put in as our lower bound? Well, these are heights. So we could just put a lower bound of a height of 0. You could also put in a height of -200, okay? In theory, this extends forever in this direction, which is a little bit silly because these are a distribution of heights. But let's just do this really quick, right? So as a lower bound, I'm going to put in 0. As an upper bound, I'm going to put in 60, I think, yep, 60. My mean is 68.1, and my standard deviation is 3.4. All right, so this is going to give me the percent, or better yet, the proportion of the students that lie between 0 inches tall and 60 inches tall in a population that is normally distributed with a mean of 68.1 and a standard deviation of 3.4. I hit OK, and that's 0.008601. Okay, right? So whatever, it's small, all right? It's less than 1%. Let's now do the same thing for the upper bound, and remember the upper bound is all these heights from 75 inches and above, 75 inches and above. So if I go back in and I go to Menu, Statistics, Distributions, Normal CDF, now my lower bound is going to be 75. That's the smallest height. What's my upper bound? We're talking about the heights of people. 200 inches is ridiculously tall for a person, in fact, way taller than the tallest person ever, but I'm still going to put it in because I can just put in a huge number there. And it doesn't really matter. So I've got now all the people that are going to be between 75 inches tall and 200 inches tall, right? Again, you could put really anything in here as long as it's a pretty big number. Mean of 68.1, standard deviation of 3.4, hit OK, and now 0.021028. Now I need to add these two together. Luckily on my calculator and many of these calculators, I can just simply do this plus this, enter. That's 0.0298, right? So I'm going to do 0.0298, etc. And that is 2.98%. All right. Last year's exam had a very similar problem, except that was just between two values. When it's just between two values, nice and easy. When it's sort of less than one or greater than another one, that's when it becomes a little bit trickier. All right, let's head on. Another normal distribution. This is one that I had to think long and hard about how to explain, so hopefully I'll do a decent job, but we'll see. Number 17. Marissa and Sydney are trying to determine if there are enough interest in their school to put on a senior musical. They randomly surveyed 100 members of the senior class, and 43% of them said they would be interested in being in a senior musical. Marissa and Sydney then conducted a simulation of 500 more surveys, each of 100 seniors, assuming that 43% of the senior class would be interested in being in the musical. The output of the simulation is shown below. All right. So again, this is interesting. We're going to run into simulation a few times on this particular test. So just sort of understand the bigger picture here. You know, we've got this random population. 43% of them would be interested in being in a senior musical. So what we do is we pretend we've got like 100 people out there. 43, or we have a huge population out there. 43% of them want to be in this musical. So then we sort of randomly grab 100 people out of that, and we see how many of them want to be in the musical. Now, most of the time, the proportion will be around 43%, but sometimes it'll be higher. You know, this goes all the way up to about maybe like 56%, right? And sometimes it'll be a little bit lower. It goes as low as 28%, but most of the simulations, right, are right around 43%. So then the question becomes, what is the standard deviation of the simulation closest to? All right. Well, all of these simulations, all of them, will generally speaking have a normal or bell curve distribution. All right. Now, one of the things that you were supposed to learn in the normal distribution work is that within one standard deviation on both sides, one standard deviation, there is about 67% of all the data. Okay, within one standard deviation. Within two standard deviations, and maybe I should have drawn that a little bit closer. Within two standard deviations, so if I go one more out, within two standard deviations, there's about 95% of all the data. Okay, within two standard deviations. And within three standard deviations, one more out, within three standard deviations, there is about all of the data, 99%. Okay, all right? So if I've got a normally distributed situation, and I go three standard deviations above the mean, a standard deviation is like a yardstick. I can like measure, okay? So if I go three standard deviations above the mean and three standard deviations below the mean in a normally distributed population, I'm going to get almost everything. So watch this. Right in the middle is 0.43, 0.43. Now, the lowest value on here is right around 0.28. That's about the lowest value, all right? So if I did 0.43 and I subtracted 0.28, what I would get is 0.15. Okay, that's the distance from the center of my distribution all the way out to sort of this left-hand tail. And that should be just about 3 standard deviations wide, right? Because I should be getting all of my data within 3 standard deviations above and 3 standard deviations below. So 1 standard deviation should be this number divided by 3, and that is 0.05. All right, and you could have done it with the upper one. So in other words, you could have said, well, let me do, maybe 0.57 minus 0.28, or maybe 0.60 minus 0.28, and then divided by 3, and you would also get right around 0.05. All right? Versus, you could also do it the other way around, which is take your mean and add 3 times the standard deviation and subtract 3 times the standard deviation and see which one of them sort of puts a box closest around the data. All right? But if you take half the width of the data and you divide by 3, you should have a good approximation of the standard deviation. Let's take a look at number 18. For f of x equals cosine x, which statement is true? All right, and then they have all this stuff about even and odd functions, even and odd functions. So let's begin with that. Let's talk about what even functions are and what odd functions are. Now, there are lots of different ways that we categorize functions. We got your linear functions and your exponential and your quadratic and your trigonometric and your logarithmic and your even and your odd and your power and your, so much, right? So many different classifications. Even and odd are one more type, right? And they can really be thought of very nicely in terms of symmetry. So an even function is symmetric across the y-axis. All right, so in other words, if I had a function that maybe looked like this, okay, that would be an even function. It looks exactly the same on the right as it does on the left. That's an even function. An odd function, so yeah, I'm going to take advantage of this right now to review both of these. An odd function is one that is symmetric. Boy, ew, man, I cannot write the word symmetric. Let's try that again. Symmetric across the origin. All right, origin. Origin, there we go. All right, and that is maybe one that would look more like this. Wow, why did I have to make it confusing, Kirk? That was weird. Yeah, that's not quite right. One low. Yeah, okay, well, whatever. Yeah, that just didn't work. It's like this. This is it. All right, so in other words, that's the worst drawn odd function ever. If I rotated this thing, this would go up there, this would come down here. If I rotated 180 degrees about the origin, I have to choose the hardest odd function ever. An easier odd function would literally be like something like this. That would be a good odd function, but I didn't go with that. Anyway, so an odd function is symmetric across the origin, an even function is symmetric across the y-axis. So what's cosine x, right? All right, because that's really where we're coming from here. We're talking about cosine x. Now, if you've forgotten what cosine x looks like, this is not a terrible time to remind yourself of its graph. So, maybe I just go into this thing, right? And I say, well, let's just do a graph. Let's just put cosine x in. All right, now, unlike geometry, which we just had a review for, in Algebra 2, you make sure your trig function is in radian mode, okay? Because all trig graphing occurs in radian mode, not degree mode. So I'm in radian mode. I'm just going to go into trig. I'm going to grab some cosine, hopefully, and hope that my calculator stops freaking out. Cosine x, and I'm going to hit enter. All right, now I could try to get the x-axis in its beautiful little form and whatnot, but I don't need it. That's perfectly good. There's cosine x. Okay, awesome, I have cosine x. Now notice, cosine x is itself an even function. It is symmetric across the y-axis. Side note, sine x is an odd function. It is symmetric about the origin. Now, let's take a look, though, at all the rest of these things. So, right, if I look at choice 1, notice it says 2 times f of x and f of 2x are even functions. This is all about transformations and even and odd functions. Well, watch this. This is really cool. All right, I bet many of you didn't even realize you could do this on your calculator. Watch what I can do. I'm going to go into menu. I'm going to go into graph edit, into my function, and in f of 2 of x, there's this little vars button on your calculator right here. I can choose f1, and I'm going to put in, actually I'm going to put right in front of it 2 times f1 of x. And remember, f1 of x is cosine x. And there's now f2. f2, which is just a vertical stretch of f1, that's still an even function, right? And the other one, remember, was f of 2x. If I did menu and I went into graph entry edit, here we go. Let me now do vars. Now I got to choose f1, not f2, of 2x. And let me do this. That's the one in black there. And notice that one, right, just sort of like accordion my cosine graph. I don't think that's a verb, but take an accordion and like smoosh it in, right? So this one took cosine x, right, and it horizontally compressed it by a factor of 1/2 or a factor of 2, depending on how you look at it. But it's still an even function. It's still symmetric across the y-axis, right? And again, you could like think about all of these sort of step by step by step, but the plain fact is the correct answer, that didn't work, the correct answer is that both of these are even functions, right? Side note, think about this. If you had an even function and you added 2 to it, it would just shift it up and it would still be symmetric across the x-axis or across the y-axis. Vertical shifting will not change whether a function is even or not. Now don't get me wrong, it will change whether a function is odd, but it won't change whether a function is even. So this is choice 1. Little even odd work there. All right, number 19. The solution set of x plus 3 divided by x minus 5 plus 6 divided by x plus 2 is equal to 6 plus 10x divided by x minus 5 times x plus 2 is which of the following? Well, one of the things that's kind of cool about this problem, even though it's a rather lengthy multiple choice problem, not as bad as the regression one, but even though it's rather lengthy, one thing that you should certainly be able to tell is some choices here that absolutely cannot be correct. For instance, I can look and immediately I know this one's out and this one's out. Why do I know those two are out? I know that those two are out because they both include the choice x equals 5. But x equals 5 cannot be a solution to this equation because it would make this denominator 0 and that denominator 0, right? And anything that makes a denominator equal to 0 when solving an equation is an extraneous root. All right. By the way, you also couldn't have x equals -2 because it would make that denominator 0 and that denominator 0. But given that -2 isn't part of any of these solution sets, it's nothing to worry about. So therefore, the answer is either just -6 or -5 comma +6. Anyway, just for the moment, well, I guess I'll leave it like that. So how do we generally solve one of these equations? Well, notice here we've got a denominator of x minus 5. Here we have a denominator of x plus 2. And here we have a denominator of x minus 5 times x plus 2. So what I end up doing is I end up multiplying both sides of this equation by x minus 5 times x plus 2. Now what that does, when I distribute this thing through the left-hand side, is first the x minus 5's cancel, and I'm left with x plus 2 times x plus 3. Then the x plus 2's cancel, and I'm left with 6 times x minus 5. And on this side of the equation, both these cancel, and I'm left with just 6 plus 10x. All right, this is what's known as clearing the denominators out. Some of you might have just gotten a common denominator for all of them and then set the numerators equal. That would have resulted in this as well. Now what I have to do is I just got to clean it up. I've got to multiply these two things out. That's going to be x squared plus 5x plus 6. Got to multiply all this out. That's going to be 6x minus 30. Man, that red pen is really loving it tonight. This thing, nothing I can do with it. Let me gather up like terms on this side of the equation. That's going to be x squared plus 11x, and that's 6 minus 30 is minus 24. This side of the equation, I have 6 plus 10x. All right, anytime I have an equation that's got an x squared in it, I'm going to be biased towards getting it equal to 0 and using factoring to solve. So I'm going to move everything from the right-hand side, the 6 and the 10x, over to the left-hand side. That's going to be x squared plus x. Minus 30 is equal to 0, right? When I subtract a 6 and when I subtract a 10x. Now I can factor that thing. Two numbers that have a product of negative 30 and a sum of positive 1, x plus 6, x minus 5. That gives me two solutions. Those solutions are x equals negative 6 and x equals positive 5. As we have already talked about, x equals 5 has to be rejected out of hand because it immediately is an extraneous root, but because it makes that denominator and that denominator equal to 0, which means the only solution to this equation is choice 1. All right, Cool. Let's take a look at problem number 20. Excellent. Here we go. Problem 20. Given x and y are positive, which expressions are equivalent to x cubed divided by y? All right. Excellent. I love this problem. Now, there's a lot of different ways to think about this problem, okay? But ultimately, this is an exponent manipulation problem, and you're expected to understand fractional exponents, negative exponents, how they relate to fractions, all of that. So I think that the easiest thing for me, at least, in terms of explaining this to you all, is taking this thing, x cubed divided by y. I recognize that this is the same as x cubed times 1 over y, so that's the same as x cubed times y to the negative 1. So ultimately, right, the thing that I'm really trying to think about is, are any of these expressions equivalent to x to the third times y to the minus 1? Well, the first one, right, which is y over x cubed to the negative 1, is going to be y times x to the negative 3 to the negative 1. Whenever we have a product raised to an exponent, that exponent gets applied to both products, so that's going to be y to the minus 1, and then x to the minus 3 times minus 1, so that's going to be x to the third, and those two things are in fact the same, right? Y to the minus 1 times x to the third is the same as x to the third times y to the minus 1. So choice 1 is correct. All right, second one. Here I've got the cubed root of x to the ninth, so that's going to be x to the ninth to the 1/3 times y to the minus 1, right? So the cubed root is the same as the 1/3 power, but now I can multiply these two powers together. 9 times 1/3 is 3, so that's going to be x to the third times y to the minus 1. And that is equivalent as well. All right, now for our real ugly one. Here we've got x to the sixth times the fourth root of y to the eighth divided by x to the third y to the third. And that's probably pretty tough for you to even see. So let me kind of like try to write it out a little bit better. And I'm going to change some things right now. I'm going to have y to the eighth raised to the 1/4. And then I'm going to have x to the third, y to the third. All right, so the only thing I really have to do immediately is do that y to the eighth to the 1/4, and that's going to be y to the second, all over x to the third, y to the third. Now I can use my subtraction property. That's going to be x to the 6 minus 3 times y to the 2 minus 3. And that's going to be x to the third times y to the minus 1. And that is equivalent as well. So it is choice 1, choice 2, and choice 3. Awesome. Okay, let's take a look at 21. Given the inverse function f inverse of x equals 2/3 times x plus 1/6, which function represents f of x? All right, I hate it when they do this. This is so stupid. All right, so they gave you the inverse and they want the original function. You're going to do exactly the same thing as if they had given you the function and they asked you for the inverse. Why? Because the inverse of the inverse is the original function. All right, if you have two functions, if you have a function that has an inverse function, then the inverse of that function will be the original one. So what I'm going to do is what I always do when I find an inverse function. I'm going to switch x and y. So I'm going to start with x is equal to 2/3 times y plus 1/6. All right. I'm going to subtract a 1/6 from both sides. Okay. And now I'm going to multiply both sides by by 3/2, not by 2/3, and I have to be very good about distributing it. So I'm going to get y is equal to 3/2 times x minus 3/2 times 1/6. All right, I can do a little canceling there, and I'll get 3/2 x minus 1/2 times 1/2, which is 1/4. Of course, if you feel uncomfortable with multiplying 3/2 times 1/6, there's absolutely nothing wrong with taking your calculator out and doing that product, okay? You definitely don't want to get the wrong answer here simply because you don't know how to multiply two fractions. The biggest mistake that students, of course, will make on this is that when they multiply both sides of the equation by 3/2, they'll forget that they have to distribute the 3/2 to both the x and the 1/6. If you don't do that, of course, you get 3/2 x minus 1/6, and you end up circling choice 4, which is incorrect. And they know a lot of students are going to do that. They'll always have that incorrect choice there, so be careful about it. All right, let's take a look at 22. How many equations below are identities? All right, well, let's begin by just discussing what in the world this means. Wow, that was kind of cool. Let's try that again. Let's discuss what in the world this word means. All right, there are lots and lots of equations that you've come across in math, okay? Lots of equations. All right, and many times you solve those equations for x or y or whatever for the one value or two values or three values that make the equation true. Identities are equations that are always true. So as a very simple example, okay? If I had something like this, this is an identity. Okay, meaning that if you took any value of x under the sun, 0, -11, 22, pi, it doesn't matter. If you took any value of x and you put it into the left side and you evaluated what 15x plus 10 was, and you put it in the right side and evaluated what 5 times 3x plus 2 is, those two things would come out to be equal, always. So an identity is an equation that is always and forever true, no matter what values you pick. So, how do you decide which, if any of these, are identities? Well, I think that the easiest way to do it is by picking convenient values of x and y and testing them out. Now, I would stay away from x and y values of 0, okay? 0 can really mess with you, okay? But you know what I love on this? I like x and y values that are both equal to 1. All right? Why not? It's got to be true for everything, right? It's also got to be true for y equals 10,000 and x equals -17, okay? But I might as well go with some easy ones. So let me put 1 and 1 in for the first equation, right? And I'll kind of drag this one out a little bit. But if I put 1 and 1 in here, I'd have 1 squared plus 1 squared is equal to 1 squared minus 1 squared plus 2 times 1 squared. Well, that's going to be 1 plus 1 is equal to 1 minus 1 plus 2 squared. That's going to be 2 is equal to 0 plus 4, and 2 is equal to 4. Well, that's not right. All right, and because it's not right, that first one can't be an identity. All right? Now, that first one will be true for certain values of x and y, but an identity has to be true for all values of an x and y, and so since I chose a nice simple one to test it with and it failed, it is not an identity. All right, so number one, that thing is not an identity. Great, let's do the next one. All right, so the next one, I've got 1 cubed plus 1 cubed is equal to 1 minus 1 plus 1 squared minus 1 times 1 plus 1 squared. So 1 cubed is 1, 1 cubed is 1, 1 minus 1 is 0, 1 squared is 1, 1 times 1 is 1, 1 squared is 1, great. So I get 2 is equal to 0 plus 1, 2 is equal to 1. No, 2 is not equal to 1, right? So the second one is not an identity because 2 is not equal to 1. All right, let's try the third one. We're very quickly realizing the answer is not 2 or 3. So last one. So x to the fourth plus y to the fourth. So we have 1 to the fourth plus 1 to the fourth equals 1 minus 1 times 1 minus 1 times 1 squared plus 1 squared. 1 to the fourth is 1, 1 to the fourth is 1, 1 minus 1 is 0, 1 minus 1 is 0, 1 squared is 1 plus 1. So 2 is equal to 0 times 2. Well, one of the most important ideas in all of math is what's called the zero product law. And if I multiply anything by 0, this isn't addition. This isn't 0 times 0 plus 2. This is 0 times 0 times 2. That's 2 is equal to 0. That is also no. That is also not an identity. And that means the correct answer is choice 4. None of these things are identities. All right. Now, for one of the most technical problems on the test, problem number 23. If a focus of a parabola is 0, 6 and the directrix is y equals 4, what is an equation for the parabola? All right. This is a particularly tricky problem. This is something that you probably worked on for 1 or 2 class periods. It's what's called the focus directrix definition of a parabola. The focus directrix definition of a parabola. So, a little reminder. All right. One of the ways that you can define a shape called a parabola, okay, is with a point and a line that the point's not on. Now, the point, it's what's called the focus of the parabola. That's different than its vertex. And then directrix is that line. All right. Now, what is the point? Well, the point is then the parabola is defined as being all the points that are equidistant from the directrix and the focus. All right. One of the most important points, whoops, that's not what I want. One of the most important points is the vertex. The vertex will always sort of be halfway between the directrix and the focus, and then it'll sort of bend around the focus. The focus is also sometimes called the focal point of the parabola. All right. And again, the idea being that this distance and this distance would be the same. If I came up here and I took this point, this distance and this distance would be the same. If I took sort of a point here, this distance and this distance would be the same. All right, so the distance from the focus to the directrix is always the same. All right, so now let's kind of dive into this one. And I'm gonna, now that I did all of that, I'm gonna actually delete it just so I have some room. Okay, now there's kind of a couple different ways of doing these problems. One way of doing these problems is by really understanding that definition of distance, okay? So let's kind of get a picture of what's going on here. I just do a little graph. All right, I've got my focus at 0, 1, 2, 3, 4, 5, 6. Here's my focus. My directrix is 1, 2, 3, 4, is this line here. All right, so I've got my parabola, and it's really going to look something like this. All right. Now, how do I come up with its equation? All right. So, first, we could do it purely by what's called the distance definition. Okay? And the distance definition would say, well, if I were to take a point and just locate it on my parabola, let's call it x comma y, then this distance and this distance would have to be the same. Okay? So how can I work that out? Well, remember, this is y equals 4. So this distance is just y minus 4. That's actually the easy part, all right? Because it's whatever the y coordinate is minus 4. That's that distance. This distance is trickier. I have to do that one with the distance formula. Now keep in mind that this point is the point 0, 6. So that distance, right, using the distance formula, is going to be the square root of x minus 0 squared plus y minus 6 squared. And that's got to be equal to y minus 4. That is literally the equation of the parabola, but of course it doesn't look like any of these. So what do? I square both sides. All right, and on this side what I'll end up getting is x minus 0 squared, which is just x squared, plus y minus 6 squared is equal to y minus 4 squared. Wow. So I'll get x squared plus y squared minus 12y plus 36 is equal to y squared minus 8y plus 16. Hoo-ha! Notice there's a y squared on both sides, so I'm going to just subtract that from both sides. That's gone, right? Now, I've got an x squared minus 12y minus 8y. I'm going to bring that 8y over to this side, all right, and that's going to give me x squared minus 4y. All right, I think what I'll do is I'll bring everything else over to the other side. So I'm going to bring that 12y to the other side, which would make it into a 4y, right? Negative 8y, sorry, negative 12y, negative 8y, positive 4y. And then if I subtract a 36 from both sides, I'll have a minus 20 there, right? So what do I end up getting here? Well, something doesn't quite look right about this. Hold on. I apologize. Let me just look at something really quick. 8y, why am I getting 12y, 8y? Yeah, I got 8y, 12y. Yeah, something doesn't quite look right here. No, I got that. Oh, it's because, yeah, hold on. Yeah, I shouldn't have the 4y over there anymore. It's just the 4y went to the other side. Sorry about that. I'm like, something looks very, very wrong. All right, so anyway, at this point, right, I'm actually really close, and I get x squared equals 4 times y minus 5. I apologize, that was horrible, which is right there. All right, now, you're probably all looking at this going, oh my gosh, right? And hopefully there's somewhere deep inside that's ringing some kind of a bell, all right? Most math teachers will hopefully show you this. They're supposed to. It's part of the Common Core curriculum, all right? But a lot of teachers will then default to a different method, all right? So after all this rigmarole, right, a lot of teachers will sort of default to the following. And this is not a criticism. I mean, obviously you just saw how ugly that was. And I kind of like got lost in the middle of it all, right? So a lot of teachers will say the following. Look, if you can figure out where the vertex is, the vertex of the parabola, let's call it h comma k, okay? Then all of these things are gonna kind of have a formula that looks something like this. And I'm going to put a little plus or minus in front of here. Y minus k equals plus or minus 1 over 4p times x minus h squared. Now remember, x is the h and k are the coordinates of the vertex, not the focus. So the vertex we'll always be able to figure out is right here, 0, 5. What is this weird p? Okay, p is what's called the focal length distance. It's the distance between the focus and the vertex, which is the same as the distance between the vertex and the directrix. In here, p is equal to 1. Often p is equal to 1. Now why is it plus minus? That's because, well, maybe the parabola opens up, maybe the parabola opens down. That all depends on where the directrix is, the horizontal line, versus the focus. Hopefully they don't give you a sideways parabola. They could. Anyway, in this case, because it opens upwards, it's positive. So what do we end up having? We end up having y minus 5. Remember, p is equal to 1 in this case. So 1/4 times x minus 0 squared, right? Y minus 5, because 5 is the vertex y coordinate, equals 1/4, 1 over 4 times p times x minus 0, also the x coordinate of the vertex, squared. Right? Now I can multiply both sides by 4, and that would give me 4 times y minus 5 is equal to x squared. Again, choice 2. All right, and that one might be a little bit more comfortable for some students. That's the way many teachers default to because the distance definition can get kind of long and complex in terms of the algebra. All right, let's do our last multiple choice problem, also kind of a doozy. All right, let me just erase that real quick, and let's take a look at problem number 24. John and Margaret deposit $500 into a savings account for their son on his first birthday. They continue to make a deposit of $500 on the child's birthday, with the last deposit being made on the child's 21st birthday. If the account pays 4% annual interest, which equation represents the amount of money in the account after the last deposit is made? All right. It's actually a pretty tricky problem. We have an entire lesson in our Common Core Algebra 2 curriculum devoted to literally this exact thing, basically. All right, so how do we think about this? Well, here's one of the keys. John and Margaret actually make 21 deposits, okay? First, they put $500 in on their child's first birthday, their son's first birthday, right? They put $500 in, And then that money sits there for 20 years, not 21 years, but for 20 years, right? Because it sits there until the child is, turns 21, right? So, and they've put it in there not when the child's born, but on the child's first birthday, right? So how much is that money worth after 20 years? Well, this is pretty easy. It's worth 500 times 1.04 to the 20th, right? But that's just the $500 that was put in there on the child's first birthday, right? Right? That's just that money, right? Then on the child's second birthday, right, they put $500 in, but then that money only sits there for 19 years, right? So after 19 years, right, the money that they put in on the child's second birthday is worth 500 times 1.04 to the 19th, right? And likewise, right, don't worry, I'm not going to do this for every single one of the birthdays, but I do want to make a point here. On the third birthday, the money that they put in, right, will only sit there for 18 years before the child turns 21. So that money is going to be worth 500 times 1.04 to the 18th, etc., right, until the child's 21st birthday when they just put $500 in and nothing else, right? So how much money is totally sitting in there after 21, or after these 21 deposits, right? Deposit on the first birthday, the second birthday, the third birthday, all the way up to the 21st birthday. Well, let's write it out, right? And now let's do it this. So on the 21st birthday, right, we've just got that 500. 1 year before that, we would have had 500 times 1.04 to the first. That's not to the first, to the first. 1 year before that, we would have had 500 times 1.04 to the second, etc., until we get to that first birthday, and that money has been sitting in there for 20 years. So we have that. All right, so that's going to give us all that money. So which one of these formulas is going to actually summarize all that? Well, this is what's known as a geometric series, right? And that's one of the few formulas where it's actually on the formula sheet and is helpful. In other words, let me try to get there, all the way down. This formula right here, A1 minus, and let me put this on full screen, not that you can probably see it that much better, maybe a little bit better, right? The sum of a geometric series is A1 minus A1 times r to the n divided by 1 minus r, right? What is r? R, right, is what's called your common ratio. I just realized for the first time that r is in italics and that one's not. Anyway, that's kind of fun. Little mistake on their stuff there. But regardless, r is something that you're multiplying by each time, right? A1 is the first amount, and then 1 is just the number 1. So if we go back now all the way to this problem. No. Come on, get up there. Here we are, right? If we get all the way back to this problem, man, there were some whoppers on this last screen, right? Our A1 is 500. Our R is 1.04. So the savings after 21 years is going to be A1 minus A1 times times R, which is 1.04. To the n. N is the number of terms you have, so that's 21, all divided by 1 minus r. Okay? And now we could factor a 500 out of both of these things just to make it look like the choice. And that will be 500 times 1 minus 1.04 to the 21, all over 1 minus 1.04. And that is choice 2. All right, that's it. And that is the end of our multiple choice problems. All right, so let's take just a little bit of a break. We've almost been going for 2 hours. My goodness, that was a lot of problems. Going with a straw tonight. I've been finding in these videos, if I just try to drink directly from the cup, it just gets all over me. Then I feel a little silly as a middle-aged man who can't drink out of a cup. So I end up with a sippy cup instead. You know, it's like a glorified juice box. So good, so good. Shout out yet one more time to Joey Chevelle, the man behind the curtain. Actually, that's not true. The curtain's back here. He's the man behind the camera. Visit jolostudios.com for the most minimalized website you can possibly get. They do web design, they do video construction, they do marketing. It's great. Also, make sure to get over to emathinstruction.com. Visit our website. You can get more instruction there. If you've got some other topics you want to brush up on in Algebra 2 before tomorrow's exam, they're there. Hopefully you won't be needing to go to our course over the summer because you will have passed Algebra 2. And we don't have anything past Algebra 2, not yet at least, on our website. Foreshadowing perhaps. But yeah, so get over to eMath Instruction's website, check it out if there's more that you need to study before tomorrow morning. Again, thank you to Joey behind the camera for his laughing at my lame jokes, and also for making sure that we have nice transitions between the camera and the board and me, and I'm in focus and all of that. Or, you know, and he's touched up my appearance. I don't actually even look like this. It's crazy. I don't know who this guy is. Anyway, so let's get on to part 2. We've got some more problems to get to. 25. The business office of a local college wishes to determine the methods of payment that will be used by students when buying books at the beginning of a semester. Explain how the office can gather an appropriate sample that minimizes bias. All right, so here's the real key. You don't have to make this really complicated, but you do have to have a pen or a writing instrument. All right, but you want to just do some very basic stuff. Now remember, this is a 2-point problem. So there's not going to be that much. You're not going to have to write an essay here. Try to get something, try to use the term random sample somewhere in your answer, and also try to make it relevant to the situation at hand. We're at a local college. So maybe something like this. Take a random sample of students entering the school's cafeteria and ask them how they buy their books. All right, so real important here. Get the term random sample in there. You know, get that in there. Make sure you have it, right? Random samples minimize bias. All right, don't just say take a sample, right? Because, you know, if you just say take a sample, it may not be a random sample, and you want a random sample to minimize bias. You know, like, make sure that you put yourself within the context, okay? Don't say I'm going to go to a local mall or a local restaurant or something like that. We're talking about the kids that are going to a particular college. Put yourself somewhere on that college campus. The cafeteria, you know, maybe the library. Maybe you just are like taking a random sample of people that walk onto campus, students that walk onto campus, okay? But make sure that you get that random sample of students and make sure it's in the context of wherever you're at. You know, don't do something weird like take a random sample of the basketball players that are on campus or anything like that. Okay, make sure you're getting sort of the big picture of all the kids that are there. All right, don't do something like only the freshmen, you know, like you gotta get a random sample of everyone. All right, let's take a look at a very straightforward part 2 problem, number 26. Determine the solution of the square root of 3x plus 7 equals x minus 1 algebraically. Now, really critical here. Remember, 2 points. 2 points, 2 points, 2 points. That's it, right? Any mistake is going to lose you 50% of the credit at least. So, square root equations, you solve these quite a bit in the course. You know, if there's stuff hanging out with the square root, get it to the other side. In this case, there isn't, so I'm going to square both sides. That's going to give me 3x plus 7 on this side, and x minus 1 squared on that side. When I square out x plus 1, that's going to give me x squared minus 2x plus 1. As I said, if you have an equation with an x squared in it, I would be biased towards getting it equal to 0 and factoring. So if I subtract a 3x minus 7 from both sides, right, I'm going to get 0 is equal to x squared minus 5x minus 6. Simple to factor this. This will be x minus 6, x plus 1. Set x minus 6 equal to 0, get x equals 6. Set x plus 1 equal to 0, and get x equals negative 1. Now think about all the beautiful work you've just done there. You know what I mean? You know that you need to square both sides in order to remove the square root, right? You know you have to get it equal to 0 in order to use the zero product law. You factored it correctly. You get all of this. Remember, this is a 2-point problem, right? And then you move on to problem 27. And do you know how much credit you've gotten on this? 1 out of 2 points, even though you've done beautiful work. And the reason why is because one of these two roots is extraneous. Now that doesn't always happen when you have square root equations, but it often does, okay? And the one that doesn't work is x equals negative 1. And I can prove it to you, right? If I take x equals negative 1 and I substitute it into this equation, right? So if I put x equals negative 1 in here, then what'll happen is I'll get the square root of negative 3 plus 7 is equal to negative 1 minus 1, and that's the square root of 4 is equal to negative 2, and that's 2 equals negative 2. Now what messes people up is they go, yeah, but I've been told forever that the square root of 4 is both 2 and negative 2. No, 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 no. Right? This is what's called the principal square root. It's the positive version. If I wanted the negative square root, there would have been a negative in front of the square root symbol the whole time, and there wasn't, okay? So this is only positive 2 equals negative 2. That one's out. If on the other hand I put in positive 6, what I would find is I would get 5 is equal to 5, and all would be good with the world. So you absolutely, positively must reject this one. You don't even need to necessarily show the check, and don't always assume that it's the negative one that's going to be thrown away. In fact, if there had been a negative in front of the square root symbol of this problem, it would have been the 6 that got rejected and the negative 1 that you kept. All right, but make sure you check to see if it's correct. Really critical. All right, let's take a look at problem number 27. The population of bacteria, P of t, in hundreds after t hours can be modeled by the function P of t equals 37 e to the 0.0532 t. Determine whether the population is increasing or decreasing over time. Explain your reasoning. Explain your reasoning, right? Sometimes problems say justify your answer. Sometimes they say explain. If they say justify, that just means you've got to have some mathematical work down that somehow justifies why you got the answer you got. If they say explain, you got to use words. You got to use words. All right? Now, that being said, right, there are a lot of different ways to do this. One way to do it is put it in your calculator, graph it, get a graph, right? And the graph will look something like this. All right, you could literally do this, get it in your calculator, and then you could say increasing because when I graphed it, the y values went up as the x values went up. That's a great way to do it. I've seen another person who literally calculated p of 0 and then p of 1 and found p of 1 was bigger than p of 0 and said it increases because p of 1 is larger than p of 0. All right? Here is another nice way of doing it, and it's what I think they really want you to do. But, you know, all of it's correct as long as you somehow get this in. So one thing that I think that they're probably looking for people to do is to rewrite this as e to the 0.0532. Do you remember earlier when we did this, we kind of unmultiplied when we had that e to the minus 5 t, and then we made it e to the minus 5 to the t? Well, now if you put e to the 0.0532 into your calculator, and you round, because you would have to round, you would find that this is 37 times 1.05464 to the t. And once we have an exponential model in this form, and by this form I mean a times b to the t, we could say it's increasing because the base is greater than 1, right? That's ultimately what we can always look at when it comes to an exponential function. Is the base greater than 1, or is it between 0 and 1? If it's greater than 1, then the exponential function increases, and if it's between 0 and 1, like 0.5, 0.75, 0.2, whatever, then it decreases. All right, let's get away from exponential functions for a moment, and let's talk about the zeros of a polynomial. 28. The polynomial function g of x equals x cubed plus ax squared minus 5x plus 6 has a factor of x minus 3. Determine the value of a. I love this problem. I've also seen this one come up numerous times on the SAT before. There is a critical idea that links the factors of a polynomial with the zeros of a polynomial. If we know that x minus 3 is a factor, then x equals 3 is a 0. Now, how does that help me, right? I'm trying to figure out the value of a. How does knowing x equals 3 is a 0 help me out? Well, what that tells me is that g of 3 is equal to 0. Literally. If I put 3 into this expression, it has to equal 0. So what happens when I put 3 in here? What does that look like? Let's take a look. So I'm going to put 3 in, and I'll have 3 cubed plus a times 3 squared minus 5 times 3 plus 6 equals 0. Again, it must be a 0. It's not a 5, it's a 0. Right, so all this is equal to 0. And notice there is only one unknown in this equation right now, and it is a. So let me clean this thing up a little bit. 3 cubed is 27. 3 squared is 9 times a. 5 times 3 is negative 15. Well, 5 times 3 is 15. Plus 6 is equal to 0. Let me kind of collect it all. 27 minus 15 is equal to 12, plus 6 is equal to 18. So I'll get 9a plus 18 is equal to 0. 9a is equal to negative 18, and a is equal to negative 2. Right? So we use this beautiful connection between a factor of a polynomial and the zeros of a polynomial, not to factor it, but to simply find a missing constant, which is rather cool. All right, let's see what's next. Okay, 29. Write a recursive formula for the sequence 189, 63, 21, 7. All right, now this is really critical. A recursive formula. There are two types of formulas that we use when we describe sequences in math. One of them is called an explicit formula. That's a formula where I can literally just plug in like the value of n, which term I'm looking for, and it will tell me the value. So for instance, something like this. A sub n equals, I don't know, 5 times 2 to the n. That's an explicit formula. Let me write down that word. Explicit. It sounds a little bit questionable, a little bit R-rated. But that is literally what it's called, an explicit formula, because I can tell you, if I said, what's my 10th term, you would just put 10 in for n, you'd do 5 times 2 to the 10th, and you'd get the value. But we want a recursive formula. And a recursive formula is a formula that you use that basically says, this is how you calculate one value based on previous values. So for instance, if I had this particular formula, let's say I had, or this particular sequence, 5, 8, 11, 14, 17, etc. This is an arithmetic sequence, right? Each term is 3 more than the previous term. So what I would do is, if I wanted to define this with a recursive formula, I would say, well, my first value is 5. And then every value is the one previous to it plus 3. That would be my recursive formula here. right? Because it's telling me how I calculate a particular term based on a term that came before it. All right, now let's talk about this, right? What's going on when we go from 189 to 63 to 21 to 7? Well, what's happening is that each time, right, we are dividing by 3. Or, if you like multiplication better, each time we are multiplying by 1/3. All right? To get to each term from the previous term, we're either dividing by 3 or we're multiplying by 1/3. So, what do I say? Well, I say my first term is 189, and every term will be my previous term divided by 3. Now, remember, this problem is worth 2 points. The biggest mistake that students make on this problem, they make 2 major mistakes. One, they don't give a recursive formula. They give an explicit formula. And there is an explicit formula. The explicit formula, by the way, is a sub n equals 189 times 1/3 to the n minus 1. That is the explicit formula, right? And they will give you, I think, 1 out of 2 points for putting that down, okay? But it's not the recursive formula. The other mistake people make is that they'll put an equals an minus 1 divided by 3, but they'll never put the first term, all right? Now that's a problem because how would you ever get the second term if you don't know the first term? You'd know the second term was the first term divided by 3, but if you don't supply the first term, then you're out of luck. All right, let's keep going. Number 30. Solve algebraically for x to the nearest thousandth. All right, well, let's talk about this equation. And I'm going to write it a little bit bigger because it's so darn small and I want you to be able to see it. 2 times e to the 0.49x is equal to 15. All right, so let's walk ourselves through this. X only shows up once. And whenever x shows up once, and only once in an equation, and you have to solve it algebraically, then I want you to unwrap x. I want you to get rid of everything that's been done to x in the opposite order in which it's been done. So let's walk through our order of operations. The first thing that's been done to x is we multiply it by 0.49, then we exponentiate, and then we multiply by 2. I now need to undo each one of those 3 things, multiplying, exponentiating, and multiplying, in the reverse order. So the first thing I'm going to do is I'm going to divide both sides by 2. That's going to give me e to the 0.49x. And look, 15 divided by 2, not the nicest number, but I think I am going to convert that into 7.5. Now, how do we get rid of an exponential? The way that we get rid of an exponential is we take the logarithm of both sides using the same base as the exponential. In this case, since its base is e, I'm going to take the natural logarithm, which is the log base e. Remember, ln of x is the same as the log base e of x. So I'm going to literally take the ln of both sides. Now, as any math teacher will tell you, you can actually use a logarithm of any base you want. But if that were 2, not e, but 2, I would use log base 2. If that was 1.05, I'd use log base 1.05. If that was 17, I would use the log base 17, because logarithms and exponentials are inverses of each other. They cancel each other out. So we would get 0.49x is equal to the ln of 7.5. And now I will divide by 0.49 on both sides. Not by 0.49x, by 0.49. So x will now be ln of 7.5 divided by 0.49, and that is just calculator work, right? All I have to do, let's go back maybe to here. Let me actually put a brand new page in just so we can have it. Calculator. Let's go here. We have the natural logarithm of 7.5 divided by 0.49. And there it is, 4.112046, etc. Be careful, right? We want to watch our rounding. Obviously, that's a place where we can easily lose a point to the nearest thousandth. That means 3 decimal places. X will be 4.112. There it is. All right, great. Let's keep going. Nice little logarithm exponential kind of thing there. Problem 31. For all values of x for which the expression is defined, write the expression below in simplest form. All right, so if they're asking you to simplify a fraction, you've got a 2-step process. Step 1, factor. Step 2, cancel. Factor, cancel, factor, cancel, factor, cancel, factor, cancel, factor, cancel. All right, now the numerator, let's take a look at how we can factor that. So let's take 2x cubed plus x squared minus 18x minus 9, and let's factor that thing. All right, the denominator is going to be easy to factor. Let's factor the numerator. This is going to be a factoring by grouping, so I'm going to look at these two and I'm going to look at these two. On that first one, I can factor an x squared out, and I'll be left with a 2x plus 1. And in the other one, I can factor out a negative 9. Often we factor out a negative, and I'll also be left with a 2x plus 1. So that's going to be 2x plus 1 times x squared minus 9. And that's going to be 2x plus 1 times x minus 3 times x plus 3. So that's the numerator. Just a little factoring by grouping, pretty straightforward factoring by grouping, right? It's pretty much the only new factoring technique you learned in this course. So I'm going to make the numerator into 2x plus 1 times x minus 3 times x plus 3. Now the denominator, 3x minus x squared, can be factored as x times 3 minus x. So let's take a look at what we have here. Now remember, it's a 2-point problem, right? It's just a 2-point problem. We haven't even made it to the 4-pointers yet. This is a 2-point problem, right? And when you look at it, it doesn't appear that there's anything that's identical in the numerator and the denominator. But one of the things we should have learned is that when we have something like this, x minus 3 and 3 minus x, those two will cancel, but they'll leave you with a negative 1, okay? So x minus 3 and 3 minus x will cancel and leave you with a negative 1. Where should I put the negative 1? Should I put it in the numerator? Should I put it in the denominator? Should I put it in both the numerator and the denominator? The answer is choose one, either the numerator or the denominator, but not both, because if you put it in both locations, then you're just putting a 1 there. You're not really putting a negative 1. All right, so what's my final answer? My final answer is negative 2x plus 1 times x plus 3, all divided by x. And that's it. All right. Now I think we've made it to our longer problems. No, we still haven't. Geez. 32, more part 2s. Here we go. An app design company believes that the proportion of high school students who have purchased apps on their smartphones in the past 3 months is 0.85. In other words, 85% have bought apps in the past 3 months. A simulation of 500 samples of 150 students was run based on this proportion, and the results are shown below. So the mean proportion was 0.852, and notice how close that 0.852 is to the 0.85. Standard deviation is 0.029. Remember our multiple choice problem where we had to try to figure out the standard deviation based on the graph? Here they gave us the mean and the standard deviation. The mean will always be exceptionally close to whatever proportion they were using to run the simulation. All right, so now what's the deal? Suppose a sample of 150 students from your high school showed that 88% of students had purchased apps on their smartphones in the past 3 months. Based on the simulation, would the results from your high school give the app design company reason to believe their assumption is incorrect? Explain. All right, so the company is assuming that 85% of all students bought an app in the last 3 months on their for their smartphone. But when you did this thing at your school, you found 88%, which is obviously not the same as 85%. Now the question is that 88% so out there that the app designers should go, well, I don't know, maybe it really isn't 85%. Maybe it's actually higher or lower, but probably higher, because of the 88%. So here's what we're going to do. We're going to construct what's called the two standard deviation interval, also known as the 95% confidence interval. What are we going to do? Well, we're going to take our notes, and we're going to take this number, our mean, always the mean here, and we're going to add twice the standard deviation to it, and we're going to subtract twice the standard deviation from it. So let's do that, and then we'll talk about exactly what that gives us. So I'm going to take 0.852, and I'm going to subtract off 2 times the standard deviation, and that ends up being 0.794. And then I'm going to take that mean, 0.852, and I'm going to add 2 standard deviations to it, and I'm going to get 0.91. I'll put a 0 there just so that we have the same number of decimals. Now, what does that mean? That means that any result between 79.4% and 91% is within the realm of possibility that just chance. So that the 85% is correct, but just by chance we got some number between these. Anything outside of that interval is so unusual that it would only occur 5% or less amounts of time, okay? So the 88%, right? The 88% falls within this interval. So it is not unusual, right? Statisticians would say it is not statistically significant. The difference between the 88% and the 85% isn't big enough to make the app developers believe their assumption is incorrect. So the answer is no, because 88% falls within 2 standard deviations of the mean. So if we fall outside of 2 standard deviations of the mean, then we are so unusual that we're occurring 5% or less of the amount of time, and therefore not likely to have occurred by chance alone, and likely there's just something wrong with our assumption. But here, that 88% falls within that interval, means it's not unusual, so the app developers have no reason to believe that their assumption is incorrect. All right, let's keep going. Now we're on to part 3. Okay, here we've got 4 questions. Each question will receive 4 credits. Now, sometimes the problems truly are 4-point problems, all right? And sometimes they're just a couple 2-point problems put together. And our first one is like that. Here we go, problem number 33. Patricia creates a cubic polynomial function p of x with a leading coefficient of 1. The zeros of the function are 2, 3, and -6. Write an equation for p of x. All right, great. Well, this is a piece of cake. Okay, I love this first part of the problem, right? If I've got zeros of 2, 3, and -6, that means I have to have factors of x minus 2, x minus 3, and x plus 6. And because the leading coefficient is 1, that is the equation of my polynomial. Now you might think to yourself, oh, do I have to multiply it all out? No, this is an equation for the polynomial. The only time I'd have to multiply it all the way out is if the question specifically said, put the polynomial in standard form. Standard form. Then I'd have to have, x cubed minus 3x squared plus 11x minus, whatever that would be. But if I just want an equation for the polynomial, that's it. And that's 2 out of the 4 points. Talk about an easy 2 points. Now sketch y equals p of x on the set of axes below. I don't love this problem. And the reason I don't love this problem is that these two zeros, x equals 2 and x equals 3, are very close together, and x equals 6 is really far apart, right? So, I can go into my calculator. There's no reason I can't, right? I can go right in, let me open up a new page, let me add a graph. Okay. Let me put that thing in. What was it? It was x minus 2 times x minus 3 times, whoops, nope, that's not good, times x plus 6. All right, there's my function. And I get this kind of looking thing. Do you know what I mean? And it's kind of ugly, you know what I mean? But there's my 0 at x equals 6, there's my 0 at x equals 2, and there's my 0 at x equals 3, right? Now, I don't even see the top of the graph or the bottom of the graph. I guarantee if you put this thing on there, you're going to lose the other 2 points, all right? You know, the graph doesn't just stop there and begin there, you know. So the problem is it's all about scale. So if I went into this thing and I played around a little bit with my window, let's say I made my window quite big, maybe like -100, no. We're keeping that at -10. I mean my Y window, because this thing stretches up big time. So -100 maybe, and 100. Let's just take a look at it. And there's my actual graph. And again, the irritating thing is, right, because of the scale issue, there's that 1 0 at x equals 6, there's that 0 at x equals 2, that other 0 at x equals 3, and the cubic just barely dips below the x-axis. Now, to be honest with you, they're going to give you full credit as long as, all right, let's get it here, as long as you've got, really? As long as you've got a giant vertical line there. As long as you've got -6, 2, and 3, as long as you've got something that's going to go like this, all right? And by this, what I mean is it's got to go through -6, label it, got to go through 2, label it, got to go through 3, label it. It's got to be going down here and up there, you're fine. But don't have stuff like this. All right, well, that's what my calculator shows me. Yeah, okay, great. You know what I mean? Just don't be my surgeon. You know what I mean? Like, that is not going to fly, okay? There's not a discontinuous graph like this. So make sure it goes through the zeros, and it's got that beautiful polynomial kind of looking graph. Okay, let's do a little probability, number 34. A public radio station held a fundraiser. The table below summarizes the donor category and the method of donation. All right, so let's kind of take a look at this thing and just make sure that we understand. This is called a dual frequency chart. All right, we've taken all these people and we've broken them up into 4 different categories. 2 of the categories are the method of donation. Did they donate by making a phone call, or did they donate online? And then donors, like these groups that take donations, always have these different categories. You're like a bronze medal, you're a silver medal, you're a gold medal. Here you're either a supporter or a patron, all right? Whatever, you know what I mean? But the point is, right, there were 400 people that donated by phone call that were classified as supporters, 672 people that donated by phone calls that are patrons, and likewise for the online. So let's take a look at the first question. To the nearest thousandth, find the probability that a randomly selected donor was categorized as a supporter given that the donation was made online. This is the most important part of this problem. Given that the donation was made online. This is what's called conditional probability. They've put a condition. I only want to know the probability given that the donation, who knows? Given that the Dalmatian donation was made online. So at this point, once they tell me, given that the donation was made online, the only thing I care about is this row. It's the only thing I care about, right? That's it. So maybe I'll add these 2 together, right? And what would that total be? That would be 3,216, right? There were 3,216 people that donated online. Now, what's the probability that somebody who was randomly selected was categorized as a supporter? Well, of those 3,216 people that went online, I don't care about the phone calls, right? I also don't care about the people who are living in Moscow, right? I'm talking about the people that donated online, right? Well, of those, 1,200 were supporters. So the probability is 1,200 divided by 3,216. Since we want that to the nearest thousandth, we've got to do that on our calculator. So we're just going to go right back, maybe here. Yeah, that works for me. And we're going to say we've got 1,200. Let me go into my fraction. 1,200 divided by 3,216. Do control approximate. There we go. I want it to the nearest thousandth. That's 3 decimal places. And that's 0.373. Again, watch your rounding. It's a shame, shame, shame when people do everything correct and then they round to the nearest hundredth and they lose a point out of 2, because this would be only 2 points and you'd lose 1 out of 2 if you put 0.37. Now that being said, let's make sure that we can just interpret this. What this tells us is that of the people who donated online, 37.3% of them, 37.3% of them would have been classified as supporters. Easy. Now let's talk about the second part of this problem. Do these data indicate that being a supporter is independent of donating online? Justify your answer. Is being a supporter independent of donating online? Well, we know that of the people that donated online, 37.3% of them were classified as supporters. If being a supporter is independent of donating online, then it should make no difference whether we donated using phone call or online. So what I'm going to do is I'm going to do the exact same probability calculation I did up here, except I'm going to figure out the probability that somebody who made a phone call and gave was a supporter. So let's just take a look at that, right? That would be a total of 1,072, right? So let's figure out the probability of being a, whoops. Let's figure out the problem. I cannot get that P to work. A supporter, right, given that they gave with a phone call. Well, all the people that gave with a phone call was 1,072. Of those people, 400 of them were classified as supporters. All right. Now, if I take my calculator out and I work out what that is, right? So I just go in and I do exactly the same thing. I've got 400 divided by 1,072. That didn't help. And I get 0.37313, etc. Huh. So 37.3% of all the people that gave with phone calls were classified as supporters. 37.3% of all people who gave online were classified as supporters. So it doesn't seem to matter whether you gave online or you gave via a phone call, right? The probability that you would be a supporter, or the percentage of those that were supporters, were the same either way. And therefore, being a supporter is independent of the method in which you donate. So how do you actually summarize that? Here again, let's put down 0.373. Let's go back into here, full screen. And now let's say, yes, they are independent because the probability of being a supporter doesn't change There we go. Yep. Now again, like if, let's say 50% of people who gave via phone call turned out to be supporters, maybe they're older or something like that. Maybe they have just more wealth that they can, donate or whatever, right? And because they're older, maybe they prefer to use a phone as opposed to donating online, something like that, right? So maybe that was 50%. Then we would say, oh, they aren't independent because there's a greater percentage of people that give with phone calls that are supporters, or whatever, all right? But in this case, because those probabilities are identical, that means that the two things are independent. All right, we're getting there, folks. Number 35. Algebraically solve the system. X minus 2 squared plus y minus 3 squared is equal to 20, and y is equal to negative 2x plus 7. All right, for the record, not that you need to actually know this, but this first thing is an equation of a circle with a center at 2, 3 and a radius of the square root of 20, whatever. And this, of course, is a line, right? So what I'm going to look to do right now is I'm going to substitute this equation into this equation. I'm going to do some algebraic magic, and we're going to come up with the two intersection points of this line with this circle. So let's do it. I love just some good old algebra. So I'm going to take my negative 2x plus 7. I'm going to substitute it in right there. Here we go. X minus 2 squared plus negative 2x plus 7 minus 3 squared is equal to 20. All right, I'm going to do a little bit more simplifying before we do any kind of like squaring out. This is going to be negative 2x plus 4. Quantity squared is equal to 20. Now, some of you might be able to square both of those two binomials in your head. Some of you might not be able to square either one of them in your head. If one of them is more challenging than the other one, it tends to be this one. So obviously, if you have to do this for either one of them, feel free to bring them over to the side and kind of just multiply them out by using a FOIL method or something like that. Negative 2x times negative 2x is positive 4x squared. Then I'm going to have negative 8x and another negative 8x. And then a positive 16, so all of that is 4x minus 16x plus 16. All right, so anyway, I'm going to square this one out in my head. That's x squared minus 4x plus 4. This is the one that we just did, 4x squared minus 16x, hello red, plus 16 is equal to 20. Hoo-ha! Let's gather up some like terms. X squared and 4x squared is 5x squared. I have a negative 4x and a negative 16x. That's going to be a negative 20x. I've got a positive 4 and a positive 16. That's going to be plus 20. And then I have another plus 20 over here. As I've now said twice already, but let's go for a third time. Anytime I have an equation that I'm trying to solve where there's an x squared, I like to get everything equal to 0 and try to use the zero product law, i.e. factoring. So I'm going to subtract a 20 from both sides. That's kind of cool because it gets rid of it on both of these sides. That's going to leave me with 5x squared minus 20x is equal to 0. Ironically, this is the easiest factoring you could possibly be asked to do on the test, and yet some people will have a hard time with this. This is just going to be GCF factoring. I can factor a 5x out of both of these. That'll give me 5x times x minus 4 is equal to 0. That means I'm going to have 5x is equal to 0, and I'll divide both sides by 5 here. 0 divided by 5 is equal to 0. So one of my roots is 0, and x minus 4 is equal to 0. Add 4 to both sides, x is equal to 4. All right. So we're almost there, right? We've got our two x coordinates. Now we need to get the y coordinates that go with this. We can take those x coordinates and we can substitute them into either one of these two equations and solve for y. If you're going to put them into that first equation and solve for y, good luck to you. Have fun. It's also going to give you two answers that are incorrect. It'll give you 4 answers and 2 of them are wrong. Just put them into the line for goodness sakes, right? Y equals negative 2x plus 7. This is your winner. Make sure to put them up in here. So when I have x equals 0 and we have y equals negative 2x plus 7, that's going to be y equals negative 2 times 0 plus 7. That's going to be 7. So that's the intersection point 0, 7. And likewise here we'll have y equals negative 2x plus 7. Let's substitute the 4 in there. Negative 2x times 4 plus 7. That ends up being negative 8 plus 7, which is negative 1. So that gives me a coordinate point of 4, negative 1. All right, there we are. Solve that system algebraically. Okay, are we on to the last problem or not? We're on to the last 4-pointer, but then we got the trig problem. All right, let's take a look at number 36. On a certain tropical island, there are currently 500 palm trees and 200 flamingos. Love it. Suppose the palm tree population is decreasing at an annual rate of 3% per year, maybe due to the flamingos, and the flamingo population is growing at a continuous rate of 2% per year. Write two functions, p of x and f of x, that represent the number of palm trees and flamingos on this island, respectively, x years from now. All right, great. This is kind of nice. Some very basic, easy exponential modeling in the first part of the problem, then we'll take a look at the second part of the problem. First, let's deal with those what? We want the flamingos and we want the palm trees. So let's deal with the palm trees. Now, what do we know about the palm trees? Currently, there are 500 palm trees, and the palm tree population is decreasing. That is exceptionally important. Decreasing at an annual rate of 3% per year. But other than that, it's simple, right? So P of x is going to be 500 times 1 minus 0.03 to the x, or better yet, 500 times 0.97 to the x, right? So there is our our palm tree population. You have to watch out for that, right? If you've got 500 times 1.03 to the x, you're going to lose probably 2 points right there, right? Because that would be an increasing exponential, and they very clearly told us we were decreasing at a rate of 3% per year. Now let's talk about our flamingos. With our flamingos, we're starting at 200 flamingos. The more I say that word, the stranger it sounds. And the population is increasing, and this is incredibly important, growing at a continuous rate of 2% per year. Well, that word, a continuous rate of 2% per year, continuous rate, kicks in what's known as the PERT formula, all right? What's known as PERT, P times e to the RT, where P is the original amount, E is the number E, R is the rate in decimal form, not 1 plus the rate, just the rate in decimal form, and T is time. In this case, we're going to actually have an X. So our flamingo population is actually 200, whoops, make that look like a 0, 200 times e to the 0.02x. Not to the 1.02x, just the 0.02. Now, by the way, if the flamingo population had been decreasing, let's say by 2% per year, this would be e to the minus 0.02, okay? So with the PERT formula, you don't do that 1 plus or that 1 minus stuff. It's e raised to the RT. If r is an increasing thing, if it's an increasing, right, then r is positive, and if it's decreasing, r is negative. But here are your two functions. There they are. Now, let's take a look at this next one. State the solution to the equation p of x equals f of x rounded to the nearest year. Interpret the meaning of this value within the given context. All right, so we're trying to solve an equation. Specifically, we're trying to solve p of x equals f of x. So we're trying to solve this equation, 500 times 0.97 to the x is equal to 200 times e to the 0.02x. Now, you've learned a lot of different algebraic techniques this year, and there is a very kind of tricky way of solving this algebraically, but it's tricky. And I gotta think that almost none of your math teachers showed you how to do it, right? You can take logarithms all you want, and this is gonna be a challenging problem, right, if you're not doing it graphically. So this is a situation, notice they don't say solve this equation algebraically. They just say state the solution. They don't tell you how to find it. You know, in fact, they're just gonna take x equals blank, and then if you give the correct interpretation, they're gonna give you a whole credit. But the best way to solve this is solve it graphically. Solve graphically. Now, maybe sometimes that's easier said than done. So let's take a look really quick at how we can solve this graphically. I'm going to actually just put in a brand new, let me do File, New Doc. Don't worry about that. Let's add in a graph. Okay, we've got two functions, right? One of them is that decreasing palm tree function. That's 0.97 to the x. Don't forget things like to the x, right? The other one, come on. The other one is going to be our increasing flamingos, 2 times e to the 0.02x. All right, and notice, I don't see anything, right? I also don't particularly love this grid. I'm going to take that off real quick. I'm going to go into my settings. I'm going to take no grid. Okay, great. I still don't see anything, right? But think about this. We started off with a population of palm trees at 500 palm trees and flamingos at 200 flamingos. Of course this doesn't show us anything, right? It doesn't show us anything because the y-axis goes up to 7. All right, so let's do this. Let's go into our menu. Let's go into our window settings. Now, I don't know about this, but I don't need any 0 on my x. And I don't know, let me go to 50 on, because we're talking about years here, right? I don't worry about my scale. My y minimum, I'm going to go 0 here. We're talking about the number of palm trees and the number of flamingos. And remember, the maximum amount I had of either one of them was 500, so maybe I'll go a little bit bigger and go 600 there. And now I see something, right? Now I've got this beautiful graph that's showing my decreasing palm tree population and my increasing flamingo population. And what I want to know is where they're equal. And that's at the intersection point. So what am I going to do? I'm going to go into Menu, Analyze, Intersection. I'm going to bring my little magic line here. That's my upper bound, Enter. And these things intersect at 18.16, 287.6. So what is the solution to that equation to the nearest year? X equals 18. All right. Now, believe it or not, they didn't even require having the graph. I would severely recommend having the graph. It shocks me that they didn't require that. But I would just have a little graph, maybe indicate some scale. I've got 600, I've got 50, I've got X, I've got this particular graph, that was my, my palm tree. I don't have to have its equation. I could just do P of X. I've now got my F of X. Right, put my intersection point on there. That was 18.2, 288. All right, so X is equal to 18. All right, rounded to the nearest year. Now, 4-point problem. This is 1 out of the 4, right? Interpret the meaning. Well, let's put it bluntly, right? In 18 years, the number of flamingos and the number of palm trees will be equal. I don't know why that's important. Maybe flamingos live in palm trees. I don't know. I'm from New York. There are no flamingos or palm trees here, except in zoos. All right, so after 18 years, the number of flamingos and palm trees will be equal. And that is my interpretation. After 18 years, the number of flamingos and palm trees will be equal. Awesome. And now, let's do our final problem. All right, so we got a part 4 problem, one problem worth 6 points. I don't know what it's going to look like tomorrow. Do you know what I mean? It'll be a challenging problem. I think this one's actually a little bit on the easier side, and we've been kind of waiting for this one. So let's take a look. Number 37. The volume of air in an average lung during breathing can be modeled by the graph below. All right, and actually let's kind of take a look at this graph. Let me move this out of the way. We can just get it all the way on the board. Okay, so this is kind of cool, right? Clearly a trig graph. Right, and we'll get to the actual question in a little bit. Clearly a trig graph, right? We can see that we're talking about it completes a complete cycle in 5 seconds, right? Starts at its midline, goes to its maximum, back down to its midline, its minimum, back to its midline, all right? One thing that's really important in situations like this, understand your scale, all right? The y scale is probably even more important than the x scale here, right? Just take a look between 2,000 and 3,000, right? We have 1, 2, 3, 4, 5 spaces, which means that each one is worth 200. All right, that's critical. The y scale is by 200s. So I've got, 2,200, 2,400, 2,600, 2,800. The y scale is by 200s. Okay, and that's really critical. So now let's go down here. Let's take a look at the first part of the problem. Using the graph, write an equation for n of t in the form of n of t equals a times sine of bt plus c. Awesome. Man, you can't get any better than this. You should have spent weeks trying to come up with equations of sine and cosine functions. And you should know what each one of these things stands for, but let's take the easy ones first. The c, which is the midline, and the A, which is the amplitude. Now normally you have to do some like work to figure these out, but here it's actually quite simple, right? The C is the midline, right? So y equals C is our midline, and in this case it's a piece of cake because C is just 2400. Right? That is our midline. It's going up above 2400, below 2400, above 2400, below 2400. How much is it going above and below? That's our A value. That's our amplitude. All right? And that is literally this distance. Right? That is A. Now, it's easy to look at that and go, oh, A is 200 because there's two, units here and 2 units here, but each one of them is worth 200. So actually, A is 400. All right, A is 400. Simple enough. Now, B. B is what's known as the frequency. It's also known as the angular frequency. That's what physicists would like us to call it. They call it the frequency, something a little bit different. But regardless, how do we figure out B? Well, one thing that we know is what's called B times P equals 2 pi. The relationship between what's known as the frequency and the period of the graph. And we're going to see this on the back side of the sheet, right, before the problem's over. Now, the period is the horizontal distance it takes for the thing to repeat itself. The period here is 5 seconds. All right, P is equal to 5. I almost don't mind the red in this case. It's just going to keep coming back anyway. P is equal to 5. So B, 5 times B is equal to 2 pi, and that means B is 2 pi divided by 5. So what is our final equation? N of t is equal to the amplitude, 400, times the sine of 2 pi over 5 times t, don't forget that t, plus our midline value, 2400. And notice again what that means, right? We kind of talked about this early on when we had, I think, the temperature variation based on month, right? Our maximum, 2400 plus 400 is 2800. That's occurring right there. Our minimum would be 2400 minus 400. That would be 2000. That's occurring right there, right? Now, one of the great things about a problem like this is you can be pretty confident whether you got it right or wrong. And the reason why is that you can very easily put this into your calculator, right, with the same scale as what they have. So in other words, like if I actually go in to my window on this, right, what you'll see is that, oh, I went from 0 to 5 along my x-axis. By the way, that scale was at 1/4 of a second each one. My minimum on that sheet was 0. My maximum was 6,000. That really should have said 200. I don't know why it went to 199.999999. That was a little weird, but because I didn't do that. And then that's our graph. And when we compare it to what we see here, whoops, let's go full screen so I can see it a little bit better. That's exactly what we have. Now you might say, well, but there's this little extra bit here. Yeah, I kind of wish they hadn't thrown that in, but they did. All right, anyway. But I'm confident I've got it. I'm confident I have it. Now let's go on to the other portion of this problem. Question 37 continued. The same lung, when engaged in exercise, has a volume that can be modeled by E of t equals 2000 times the sine of pi t plus 3200, where E of t is the volume in milliliters and t is the time in seconds. Graph at least one cycle of E of t on the same grid as N of t. And I actually really appreciate what they did here when they said graph at least one cycle, because in previous tests they've said things like graph one cycle and then if kids graph 2 they would take off credit. Here they're saying graph at least one cycle. Now you would have to go back to the other sheet to graph it. I put it right here. So let's talk about how we're going to graph this thing based on its equation. All right, now we're going to go in the opposite direction of what we did before. We can now say y equals 3200 is the midline. All right, so first thing I'm going to do whenever I graph one of these things is I'm going to graph the midline. And I like graphing the midline in dashed line. All right, so this is y equals 3200. Okay, that's my midline. Now, one thing that I know for certain is that my amplitude is 2,000. So that's going to go 2,000 units above and 2,000 units below and 2,000 units above and 2,000 units below. But the tricky thing is how often. So I really need to figure out my period. Now this time, right, kind of working in the opposite direction, what I know is that b is equal to pi. Okay? And remember, I know that b times p is equal to 2 pi. So if I divide by pi on both sides, my period is just equal to 2. Now make sure you really understand what that means. That means every 2 seconds, maybe I'll put the units here, every 2 seconds a complete cycle is going to get through. Remember, the original one, it was every 5 seconds we were going to go through a complete cycle. Here it's every 2 seconds, okay? Which means, and I always encourage kids to do this, do the period divided by 4, that's 2 divided by 4, that's 0.5 seconds. Every half second is a quarter of a period, all right? So what do I now do? Remember, I've got my amplitude is 2,000. So since it's the sine curve, it starts at its midline. Okay, then what's going to happen is I'm going to go a half a second. Now a half a second is right here, and now I need to go 2,000 above that. So I'm at 3,200. I need to go all the way up to 5,200. All the way up to 5,200, which is way up here, right? I need to add 2,000. Literally, this is 2,000 higher, because that's what my amplitude is. Okay? Now, let me get rid of that. Now I'm going to go another half second, and I'm going to be back down to the midline. Now I'm going to go another half second, and I'm going to be 2,000 below the midline. 3,200 minus 2,000 will be 1,200. I just need to be careful. Right there. All right, now I'm going to go another half second, and I'm going to be back to the midline, and that's going to be right here. So what does this look like? A little bit hard to get it all in. And that is one complete cycle. Now they just said at least one, so I could literally be done now. The problem is, take a look at this last piece. How many times during the 5-second interval will n of t equal e of t? I need to know how many intersection points there are, and I've only graphed one cycle. So I have to actually keep graphing these cycles. But now it should get easier, right? I'm going to go another half second. I'm going to be back up to my maximum. Now I'm going to go another half second, and I'll be back down to my midline. Now I'm going to go another half second, and I'll be back down to my min. Whoops, now I'm going to go another half second, and I'm going to be back up to my midline. Now another half second, and I'll be back up to my maximum. Another half second, and I'll be back down to the midline. Now, I've graphed now 2.5 cycles, so way more than what they wanted me to, or at least what they said I had to do. But now I can say 1, 2, 3, 4, and I'm going to say 4 times. And apropos for our last problem, the red pen comes back out, makes one more visit, which is awesome. I love me my red pen. And that is the end of this test. So let's do a little summary. Kirk's final words of wisdom, so to speak. Let me get all the way back to the beginning. All right. So, for many of you, well, maybe not many, but for some of you, right, tomorrow might be the last real math test you take for quite some time. Algebra 2 tends to be the last math class that a lot of people will take at the high school level before they'll go on and maybe take some pre-calculus or statistics or different things like that at the college level, if that's the path that you choose to pursue. The Algebra 2 test is most certainly thought of as being the hardest of the 3 Regents math exams. But as I've said before, you've got 3 hours and a wonderful graphing calculator. And there's a lot of things that we did on this test algebraically that you can then either check using your graphing calculator or just straight up do using your graphing calculator. All right? So make sure to take advantage of those 3 hours that you have. Take your time. You know, a lot of you are sitting there, you're juniors right now, and next year you'll likely be applying for colleges, right? Colleges will love to see a good grade on this test. Oh, you got an 87 on your Algebra 2 Regents exam? That's awesome. That's a really tough exam. All right, great. We're looking to admit you, right? Awesome. Not only that, but just the pride of like doing well, and well may just be passing this thing. Do you know what I mean? I'm not saying you got to get an 88. You know, hey, you get a 72 and you're happy with that. More power to you, right? The Algebra 2 exam is not easy. There is high level stuff on this, right? I bet you could give this test to like 100 adults in their like 40s, and probably most of them would fail the exam. I may have even if I hadn't been a math teacher. You know, Joey may have if he hadn't had to sit through like 6th grade through 11th grade math 18 times. You know, he kept failing. It was weird, you know. So anyway, you know, take your time tomorrow, right? And enjoy, live, like soak in the fact that when you're done with the test, in all likelihood, you're going home for the summer. Maybe you're working a pool job, or, you know, you're working at a grocery store and a pizza place, whatever. You know what I mean? You're going to hopefully hang out, enjoy the hot weather, right? And enjoy some time off from math. I know that sounds almost impossible. Time away from math cannot be enjoyable, but you will do it. Just take your time, believe in yourself, think hard about everything, remember basic principles. Now, on a broader note, I just want to thank everyone, whether you're an Algebra 2 student, an Algebra 1 student, geometry, or you're in 6th grade math. I want to thank every single student that allowed me to come into your classrooms, into your houses to give you math instruction this year and every year that I've had the privilege to do this. It is always an amazing thing to me that I get a chance to be able to stand up here and help people out with math. It is an absolute love of mine. I absolutely adore teaching people math. I love the subject. I love working with young minds, young students to help them get better. And I do want to thank all of you. I want to applaud all of you who have worked hard, from those who are in 6th grade all the way up through those who are in Algebra 2, who've worked hard this year and every year at math. It is a tough subject. It is an abstract subject. It is also a beautiful and amazingly useful subject. And I hope that all of you, no matter how old you are, will continue to study math, and you'll continue to understand how it can unravel the mysteries of the universe around us, right? The poetry of the universe is physics. But the language with which that poetry is written is mathematics. And never lose that. Never lose sight of that. Never lose a handle on that. Mathematics is the key to unlock everything from the infinitesimal to the infinite, right? And it is part of every one of us. Don't ever forget that. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.